Welcome to our Intro to Python programming tutorial. I am Rachel. I'm going to be giving this a whirl with you guys today. A little bit about me. I did my PhD in physics at Penn State and then moved to Minnesota. I've been working at MSI for a couple years now, mainly as a research data consultant, which is a fancy way of saying I'll help you with your research in any way I can. I'll do programming, I'll help you parallelize your code in the cluster, I'll do pipeline efficiency tests for you, whatever. Feel free to stop me at any time and ask questions if you want. I am absolutely happy to clarify, explain, whatever. What kind of research are y'all involved in? Just so I have sort of some framework. There's only people online. I'm staring at three people in this room.
I can start.
Yeah.
I'm Shruti. I'm actually one of the general surgery residents at the hospital
Oh,
here.
wow. Okay.
I'm in my research time,
Mhm.
and I'm in a basic science lab. Took Python a long time ago,
Yeah.
but for some of our outcomes work that we do, looking at large databases, just need some refreshers on Pythons in order to be able to go back into coding data.
Yeah, sure. Okay. Okay. So, all right. So, like database manipulation kind of stuff. We probably won't make it there today, but this will be a good refresher. Yeah.
Yeah, I'm Camilla. I'm currently a master's student in the plant pathology department.
Oh, cool.
So a lot of what I'm doing is genotyping a bunch of plants that have been collected from, across North America. And I don't really I know a little bit of like programming with R because I
Oh,
was in
sure.
the ecology department.
Yeah,
but
yeah,
I
yeah.
have no idea how to run like all of the genotyping and genetic analysis tools.
Yeah.
I'm gonna need pretty quickly.
Okay, so genotyping and a little bit background in R.
Hi, my name is Miguel. I'm a postdoc in the neurology department. So I have some experience on coding, not so much in Python. I'm just starting. So my lab is doing a lot of neurology on EEG data, big sets of data, trying to do some coherence analysis. And we usually use MATLAB, but we are right to a point that, MATLAB is too slow.
Yeah, MATLAB can be slow.
Yeah, so I tried Python a couple of things. I jumped directly to functions, but I don't know the basis.
Yeah.
I need the basis really.
Okay, yeah, absolutely. That's what we're here for.
Yeah.
The functions is like the last thing we do in this. So you're gonna get everything leading up to that. Okay, a little bit of EEG data sort of stuff. Ooh, okay, we're back. Okay, cool. So it sounds like some people have at least some limited experience with programming, which is great. Python is a very natural programming language to learn. It uses a lot of natural language. So if you have any other coding experience, this will probably come very naturally to you as well. But hopefully our people online also maybe have a little bit. Even if you don't, that's okay. That's why we're doing the intro class. We're starting from absolutely nothing. And I'm not going to assume that you know anything. But feel free to ask me like follow-up questions specific to your research if you want. Sometimes there are some specific use cases that might be helpful for you. Okay, so we have a long haul today. We're going 10 to 3, but we will have an hour-long break in there for our lunch in the middle. So we will get a little bit of a break. During lunch, feel free to ask me questions. I'll be sitting here eating my very sad packed lunch. So you can bug me if you'd like. People online, feel free to drop questions in the chat. I will do my best to sort of monitor it. I have it pulled up on a second screen here. Oh no, Brax, you use Python already in your research. Okay, well, feel free to stop me if I say something wrong. No, I'm kidding. But we also have Mo here as our co-instructor, so we've got backup if need be, and hopefully Mo will also be keeping an eye on the chat for us. Yeah, we would love for you to live code during this. The best way to learn is by doing, of course, and doing it yourself. I'm going to walk you through how to get that something that you can use Python and pulled up pretty quickly as long as you have access to our cluster. So we should be cooking pretty quickly. So first off, I had this screen up earlier, but if you haven't yet, please try to log into the cluster. Let's make sure we can make that happen. Step 1, you can either do that by opening up a terminal. Sometimes it's called a command prompt if you're on a Windows machine. Or you can access it through Open On Demand, whatever floats your boat. the open on-demand terminal access sometimes doesn't like copy paste, which can be annoying. So it is easier to access, but copy paste is sometimes helpful. Also everybody in the room right now, if you want to hop on the Zoom call, I'm going to be copy and pasting links into the Zoom chat, which will make it faster for you guys instead of having to like type out HTTP on your own machines. Right, if you have a terminal pulled up, if you're going to log in this way, on Open On Demand, it's just, let's start there. On Open On Demand, it's a simple button. So I have Open On Demand pulled up here. What you want to do is go up to clusters and then Agate shell access. And because you've already logged in with your UMN credentials, it will go ahead and boot you right into the cluster, which is great. If you want to use a terminal, then you just have to type SSH, which is basically the command for logging in securely and remotely to something, and then your UMN ID. So whatever that, 5-letter plus number combo is. And then we're going agate, which is the name of our cluster, .msi.umn.edu. And you'll get a prompt here to log in. You'll type in your password, and then hopefully you have two-factor authentication set up, and you'll also get the prompt on your phone or whatever it is to log in there. I'm not going to do that because I have Open On Demand pulled up. But either should work. So I'll give you like 2 minutes here just to make sure that folks make it. People online, if you just want to give me like a thumbs up confirmation that you're able to do this, that would be great.
Somebody would just send me oh, no, just kidding, on Zoom meeting.
Cool, okay. Got 1 thumbs up online. I'll also put in the
I'm sorry, for the using the terminal
Uh-huh.
on the cluster.
Yeah.
Just do that in a web link, or do I do that in Open On Demand?
No, so terminal is an application,
Okay.
usually on a Windows machine or it looks like you might have a
I have a
Mac.
Mac, yeah.
Yeah, so it is called terminal.
Oh, okay.
The symbol for it is like a little black box.
Oh, yeah, I see it.
Yeah. I know it looks like a hacker screen or something, but and so yeah, the command you're looking for is SSH, your ID, and then agate.msi.umn.edu.
And this is just so that you can copy paste stuff easier.
Yeah, like I said, you can do it through Open On Demand. It's a little bit faster, but you can copy paste things into the terminal screen, and sometimes Open On Demand likes to be finicky about copying and pasting into their web browser access. But they are equivalently the same. You're getting the same access, the same login.
See all the duo stuff.
Yeah. Okay, so if everyone is on the cluster, we're also going to do the most basic crash course on a command line. So whenever you log into the cluster, either through the terminal or through Open On Demand, you're getting basically a raw command line. If you're not familiar with command line coding, that's very okay. You only need to know just a little bit to make it through this Python tutorial, just enough to make a directory for us so that it's going to be easier once we open up Jupyter. So whenever you're logged into the cluster, like I am here on this Open On Demand page, ls is short for list, and it's going to tell you everything that's in the directory that you're in right now. So for us, you can see anything blue is going to be a directory, a folder. Anything white is a file, and then sometimes you get these green ones. They're also files. They're a special kind of file called an executable, but we're not going to worry about that. What I want us to do today is just make a directory so that we have it isolated for what we're going to do next. So make directory command is mkdir, short for make directory. And then you just need to put the name of the directory, whatever you want to call it. So I suggest calling it Python tutorial, but you can call it whatever you'd like. The trick here in command line is that you never want to put spaces in directory or file names. It just ruins the whole thing. And you also don't want to put any points, decimal points, periods in file names here. So you can see I already have one called tutorials right here. So is everybody good with that? I'm getting nods from the room. Can I get some thumbs up online? Okay, I'm seeing a couple. So now we need to download some files onto the cluster for you that we need for the tutorial. So we're going to go into that directory we just made using the command cd, short for change directory. And then you put in your whatever you called your directory. You can use tab to autocomplete once you start typing a directory name if you happen to make it super long. So, oops, I actually had to. Well, here, I'll just make a one here really quick. Python G. Where did I hold? Yeah, that fell 26, I think. There we go. And now we're going to use something called wget to download the files directly to the cluster. Wget takes a file at a URL and pulls it onto the cluster. This is obviously something that you want to make sure you trust the data on the other end before you do. The other way to go around this is you could download it to your local machine and then upload it to the cluster, but that's going to take a couple extra steps. So we're just going to use wget today. And I'm going to copy and paste these links into the Zoom chat. Oops, maybe not. Again. So you know, open on demand doesn't want to let me copy paste. So let's pull our terminal back into here. But the command is just wget and then the URL. So I am just doing the duo push to log in to I get here, going in up to our tutorials, Python. There we go. And we're going to do wget. And you'll see you'll get a little information about how long it's taken and stuff like that. It's super small, so it's not going to take very long. These are zip files. And we'll do the other one as well. Perfect. So now if we use ls, we should see 2 zip files. Oops. And now we just need to, oops. Yeah, sorry. Okay. Now we just need to unzip them. So you type unzip. We want code. And unzip the other one. What was the other one called? Data, I think. Yep.
Could you put the URLs back in the chat?
Yeah. Oh, yeah, sorry. That will be faster. Let's see. Yeah. Copy paste is not one. There's one.
So, sorry, I think I'm missing a step. For the unzip, did you type in something different than the URL?
Yeah, sorry. So you want to do unzip and then the name of the zip file that's been downloaded into your folder. And this is when the tab autocomplete is very helpful. So if you use ls to list the things in this directory again, we should see 2 zip files, and then now the unzip directories, code and data. How are we looking online? Are we good in the room? Yeah? Okay. Perfect. When we circulate these slides later, I've also included a second method for uploading files to the cluster that you might need or want in the future, where if you have files local on your machine, you can copy them up to the cluster. So if you don't have your files hosted somewhere on the internet, you can still copy files to the cluster and use them as you need. We don't need that today, but I did include it in the slides just in case you need it later. Okay, so now that we have everything set up in our terminal, we're going to head over to Open On Demand. Put that link in here again. UMN.edu. OOD is short for Open On Demand. And then we're going to go to Interactive Apps and down to Jupyter. Maybe. Yeah, there we go. Just take a little bit. And so then under account, you'll use whatever group name you use the most often on the cluster. I'm part of a couple groups here, so I've got a couple options. I'm just going to use my staff account. The lowest first option for resources works just fine. We're not doing anything intensive. We don't even probably need that much scratch space and that many cores, so that's just fine. You can choose between notebook and lab, whatever floats your boat. I like notebook. The Jupyter Python option will work just fine for us today. Leave all of this other stuff empty. And then we're going to want the full 8 hours because we have a long session today. If you chose something shorter, you would eventually just get kicked off because you ran out of your wall time. If you want to be super crazy in the future and you want a Jupyter notebook to persist for a really long time, you can always choose until next maintenance. This will eat up your usage on the cluster, so I only suggest doing this if you actually need it. But you can use until next maintenance if you've got something that you really want to leave up between sessions or something like that. Maintenance for us is tomorrow, so we would not get that much time on if we chose that, so 8 hours is fine. There are a couple other options down here that you might need in the future. We don't need them today. And then you can just click launch. I already have a session up, so I won't click that button, but click launch and it'll kick you to a screen that looks like this. This is a listing of all of the interactive applications you have going on Open On Demand. You can see I was using RStudio yesterday. But today you should have a box with Jupyter, and it'll probably say something like queued, maybe. Depending on your fair share usage, it may take a long time or a very little bit of time to launch for you, but eventually it'll say running, and then you can click connect to Jupyter here. So people in the room, just give me a thumbs up when you've gotten connected to Jupyter. Yeah, it's launched. Okay. Sometimes we get a couple people who come in and their lab has used all of their fair share usage and it takes it forever to launch on Jupyter. Hopefully we don't run into that today. But once we're connected to Jupyter, I'm not sure how many of you are familiar with Jupyter Notebook, but this is a really lovely instance of Jupyter Notebook because it connects directly to your account on the cluster. So if you've used the cluster before, then you should see some folders here that match the ones that you have on the cluster. This is just a nice little GUI for you to interact with them. I use the cluster all the time, obviously, so I've got a ton of things in here. But we're going to want to click on whatever it was you called that directory, so Python tutorial or, what have you. So I'm going to put here because I put all my tutorial notebooks in here. And you shouldn't see any of these tutorial notebooks, these are mine. But otherwise you should see that code data folder and then the 2 zip files that you had before. And you just want to click new. And then let's choose Python rich here. This is just the version of Python that Jupyter is going to use when you launch it. We want Python rich because it has a lot of supporting packages built in that we're going to need and or want for today. So it has things like NumPy and Matplotlib and all of the standard stuff in there. In the future, if you ever get really pro, you can also make your own kernels in Jupyter. So you can see I have a couple of special ones in here, like this OMESR one that has special installation in it for me. You can do that as well for yourself in the future if you really like using Jupyter notebooks. But then we should just get a normal Jupyter notebook page.
If we do that, will that gonna still be saved next time that we log in, or will we have to create it every single time that we log in on demand?
The Jupyter notebook?
Yeah.
So, okay, that's a great question. The question, in case people couldn't hear, is will this Jupyter notebook be saved or will it disappear every time? It does get saved. It gets saved as a normal file. So if you click back to wherever you have the Jupyter notebook screen, you can see that the untitled IPython notebook I just made shows up there. So it's now on the cluster and it's saved there just like any other file. So every time you launch Jupyter from Open On Demand, you'll be able to see it and reopen it and do whatever you'd like with it, unless of course you choose to delete it. But you can also see if I'm on the cluster now, just going back to a cluster screen. Oops. That thing did that. What do we call it? Summer and list. You can see all of the other, same IPython notebooks I've had there and the one we just made, this untitled one. So it just lives as a normal IPython file on the cluster, which you could download as well to your local machine if you wanted to. Okay, and then I'm going to give a super brief introduction to Jupyter Notebook in case people haven't used it. Jupyter Notebook works in these things called cells, which is basically just a fancy way of saying blocks of code. And they each run individually. So I can make multiple cells, enter cell below, for example. Now I've got 2 cells, and anything I type in here, print, hello, oops, hello, maybe print world. I can run this cell by itself by hitting Shift Enter, and it ran, but you see the other one didn't. So these cells each act independently, which can sometimes be very nice and sometimes be a pain in the butt if you forget to run some cell earlier in the code or something like that. And then something else that might be helpful for you today is that you can go to cell, all outputs, and clear them if you want to get rid of all of those things that it has generated already. And that's the super basics of Jupyter Notebook. There are a lot of other great features, but that's all we're going to need today. So I am going to go ahead and pull up our first tutorial here. So the way that we're going to work through the really crash course into Python today is by a pretty simple research goal. We've got this data that we've downloaded using wget, and all of that data, you can poke around at it. It's all CSV files of tabular data. And it's, oh, this is really small. There we go. And so it's going to contain rows of patients by days of inflammation. So it's just a really big standard matrix that you might run into in your research. I feel like no matter what kind of research you do, we all end up with data like this of some form or fashion. And we want to do some really basic analysis on this data, find out if there are trends, and try and draw some conclusions. And that's it. That's what we're going to try and do today. Learn enough Python to make it that far, which is actually pretty far. So this should hopefully be enough to get you through some basic plotting, being able to open files and look at the data inside, make plots of them, save those plots, and maybe even make a couple basic functions to make your code a little bit faster and or easier. So we're going to start with some super duper fundamentals, which is going to be data types. So if everybody has their Jupyter notebooks pulled up, you can start mucking about inside. PythonWorks is a really great calculator. If you just want to do some basic functions, adding numbers together, exponentiating, any sort of that kind of stuff, Python's great at that. It does it so fast and without any issues at all. And you can do that kind of thing in Python raw. So you could do it from the command line, even if you wanted to.
How are you getting it to give you outputs? Because when I hit enter on mine, it just goes to a line.
Yeah, so to get the output, you have to hit Shift Enter. Normal enter will give you a new line in your cell. Shift Enter will run the cell. You can also hit run up here, but it may run all of the cells. So that's pretty nice. I mean, having a built-in calculator, sure, why not? We can do it on our smartphones nowadays, but yeah, once upon a time that was really convenient. Not really to us, especially if we want to make some sort of expression that's repeatable. Like, let's say we want to do a calculation, store that value for later, and do something with it down the line. We're going to want to make a variable. So a variable in Python is much like a variable in any other coding language you might have done. You can type whatever you'd like to call your variable and then an equal sign and put something on the other side, preferably a number or something simple that we can do things with later, preferably a number. You can name your variables just about whatever you want. Blah, blah, blah works, or blah, blah is fine. It can be really, really long. It can be as short as a single character. There's very few limitations on what you can put in a variable name. People in Python tend to use underscores to break up words if you need multiple words in a variable name, and or camel case, which is that kind of thing. Generally, people prefer underscores. So if you're looking at Python code, people use underscores all the time. You can't put a space in a variable name because that is used by the Python interpreter. You also can't start a variable name with a number. So I can't call this like one weight. Because Python is going to see that number and think it's a number and not a variable name. And the other limitation is you can't put decimal points in variable names. But otherwise, you're free to your heart's content. So make sure you've run whatever cell you called that variable name. I called it weight because we're going to use it later. So now that we've made this variable, you can see that actually nothing prints out because we've just sort of defined this variable as whatever this is on the right. So that's where the beautiful print function comes in. We all love print. Print will take whatever you give it and print it to the screen. So if you're running a Python script that's sort of running in the background and you've got a print statement in it, it will print that to the screen that you're staring at. And so a lot of people use this to help debug their code or provide user output or user information. But it's great. It'll print the number for us. Print is a built-in function of Python. So functions will take inputs and do a variety of things to whatever you give it. Print is really simple because what it does is it prints it to the screen. But functions do require parentheses. So if I tried to do something like this, where I've just put spaces between print and the thing I'm trying to print, you're going to get an error. So almost all functions will require these kinds of parentheses around them, or otherwise you're going to get an error message, which is also a great time to talk about really briefly error messages. So in Python will try to give you as detailed an error message as it can. And especially with built-in functions, it may even provide support. So in this case, it tells us, you forgot your parentheses. Did you mean instead to put parentheses around the thing you're trying to print? So a lot of built-in Python functions will give you pretty detailed error messages like this that can give you a little bit of support. But the basic sort of way that error messages look is that it'll tell you where the error message came from. In this case, it was this IPython instance, and the line of code even that it came from. So you can go back into your code and find out exactly where the error got triggered. So this happens to be line 1, line 2, our print message, it got mad. And another brief thing about functions, it can take more than one input, typically. So print especially can take as many inputs as you want, separated by a comma and a space. So I could put this variable in here as frequently as I wanted, separated by a bunch of commas, and it would print it out as many times as I asked it to. I'm just going to stop there really quickly because that was a lot of introductory information. Any questions so far?
Yes, I do have
Yeah.
an issue with unzipping one of the files.
Oh, okay. Maybe Mo can
Yeah.
come over and help really quickly. Oops. Okay, cool. So now we've made a nice variable that we've called some number. I've set it to 3 + 4 times 10. Now we're going to talk about data types. So Python, like other programming languages, has a couple different data types, which you can always access through the built-in Python function type. So if you ever want to know what type your data is, you just type and a parenthesis and the thing. So in our case, I've called this variable weight kilograms. So I'm going to do type weight kilograms. And then I'm going to nestle that inside of our print function. So it'll print it to screen for us. So you can see that it's called a class int. Class is kind of nomenclature the same as data type. In this case, 70, the number 70 is called an int, an integer. It's an integer number. Makes sense, right? What other data types do we think there might be? People have a little bit of coding experience. So what else would you expect to see?
Strings.
Strings is a great one, right? So we can make strings using quotation marks in Python. So maybe I want to call this weight string, and I will put the parentheses around the number 70, and now it's a string instead of a number. And we can print type weight string. So even though it still contains 70, the number, because it's in parentheses, it's now a string. We could also change this to 70, for example, also a string. Anything in quotation marks becomes a string in Python. Basically, no matter what you put in it. I could put quotation marks and then like the name of our variable. And because it's in quotation marks, still a string. It's not going to be a variable anymore. What else might we run into?
Double or float?
Yeah, floating point numbers, anything with a decimal point that's not an integer, right? So in Python, anything with a decimal becomes a floating point. So I could say 70 with a single decimal point, not even with anything after it, and print the type of that. And we've got floating point numbers. These are the 3 ones that you'll run into most frequently. They cover almost everything, short of lists and arrays, which we'll get to, which are kind of collections of these data types. There are, of course, a couple other ones. The one other one that we will probably run into today is Booleans. Booleans are just true or false. That's all it can be. It's either true or false. And so if we print type weight bool, we'll get Boolean. In Python, the one other trick with Booleans is that true and false can also be represented by 0 and 1. So sometimes you can run into issues when you want an integer number 1 or the integer number 0, and it treats it as a Boolean instead. So you have to be careful about that. 0 and 1 are a special case where they can sort of be both, depending on how you manipulate them.
Do capital T's and capital F's work for calling like saying a Boolean, or does it have to be spelled out?
It has to be spelled out.
Okay.
And even if I do like lowercase, for example, not the same. I'm getting an error, right? So it has to be capital T true and capital T false. Okay, cool. So a couple things about these data types. If you take an integer and you multiply it by a floating point, it becomes a floating point. And that's to maintain as much precision as possible because a floating point number has more precision than an integer. When you multiply them together, it's going to keep the precision of the floating point number. So even though, 4,900 could easily be represented by an integer, because you had the decimal point on the 70 that you multiplied with, it's going to keep that precision. And floating point numbers take up more memory than integer numbers. So only use floating point numbers when you actually need them. Otherwise, you'll be eating up memory that you don't need to. And we can do the same thing with the string 70. This one is a fun one. It just repeats the string 70 times. So now you've got 70, the string 70, 70, 70, 70, 70, 70, 70. So be careful when you are trying to do operations with mixed data types. It will not always do what you expect. So always make sure to check your data types when you're doing what you think is math, because it might do something crazy if it's not a normal data, if it's not the data type that you expect it to be. So instead of getting, 4,900 in quotation marks, we got 70, 70, 70, 70, 70. So now we're going to do a little bit on our variables. So I still have this weight kilogram variable from before that I had set to 70. And maybe I want to use it to do some math to it. I'm going to convert it to pounds. So I'll multiply it by 2.2. And because weight kilogram, we know is an integer, it's a number, it's not a string, then I know that 70 times 2.2 should give us another integer or floating point. Floating point, right? Because 2.2 is a float, so multiplied by an integer, we'll get a float. And we can print those two numbers out now. So weight in pounds is what we expect, 70 times 2.2, 154. And we still have our original variable weight kilograms. So multiplying weight, our kilogram weight by 2.2 and setting it equal to something else, assigning it to our pound weight, doesn't change the original. And we can double check, that it is what we expect it is. And we can double check our original, still 70, right? But if we changed our weight kilograms at some point down the line, let's say we changed it to 10, we would expect our pound weight to also change, right, to 700, except it doesn't. Because in this case, we haven't reassigned pound weight yet or recalculated it. And so it still has that old number in memory, 154, because we haven't asked it to recalculate pounds. So even though we changed our kilograms, because we haven't recalculated pounds yet, it still has the old number stored. But if we asked it to recalculate it again, then of course we'll get what we expect out of it, 22. So this is where functions are really helpful, right? So if we had set weight pound to a function and we could just call it twice really quickly and get the new number out. And we can see now if I decided to change weight pounds to 100 manually, so now it's not a reference to kilograms at all anymore, that also doesn't change the original kilograms. So I'm going to stop here. Any questions about references and variables? Okay, cool. Gonna get to the fun bit. Let me clear all of our outputs here. Yep, I clicked the right one. Okay, cool. So now we get to actually look at our data that we've imported. The most common way to look and analyze, especially tabular data in Python, is a function library called NumPy. Very original, numbers Python, NumPy, right? Pretty straightforward. NumPy is used most frequently for arrays, which is a fancy way of saying matrices, which is a fancy way of saying tabular data. So in our case, we have those CSV files that contain the patients in the rows and the days of inflammation in the columns. And we're going to use NumPy to access it. I've linked an additional tutorial NumPy on here if you're interested, because NumPy is a very large and complex library that can do just about a million things, and we're only going to be scratching the surface today. So we have to start by importing a library. So in Python, in order to import a library, you use the word import, and then the library that you'd like to import. Luckily, it's super straightforward. And it's easy to remember. And as long as you have that library available, it should run without issue.
Why doesn't this have parentheses?
Because import is not a function, which is weird, right? Import is sort of a special case because it's not a standard function, and it's not treated like a function in Python, which I agree is strange. But import is one of the only exceptions here that you don't need the parentheses.
Do you want us to get to a new Jupyter?
You can if you'd like. You definitely don't have to, though. Yeah. It is standard in best coding practices to put your imports in alphabetical order. So if you had multiple imports, then putting them in alphabetical order is generally the standard. And separating them by standard libraries in a code chunk. And then if you have any custom libraries would go later in a code chunk, each one individually in alphabetical order. So you might see that sometimes, especially in like professional code, it'll be separated that way. And the other nice thing that I'm showing here is comments. Please, 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 please comment your code. So you can use a little hash here, and whatever you put after the hash is not treated as code. It's just a little note. Whatever you want. You can type whatever you want in that. As many decimal points or numbers or words as you want, and it will be ignored by Python. These are super, super important, especially if you're in a lab that passes code down between grad students, because it's your way of telling your future self or future grad students of what the heck you were doing. So I always lean on more comments than maybe are necessary, but I thank myself down the line. And you'll see me use those throughout here. Anything with this little hash in Python, you can type whatever you want afterwards and leave as many comments as you'd like. So now that we have this library loaded, NumPy, we can use it. So the way that libraries work in Python is generally you'll have to put a decimal point after the library name to pull out a function from the library. So in our case, our library is NumPy, and the function we want to pull out is load text because we've got a bunch of these CSV files. And so we do NumPy dot load text. And then load text is a function. So you got the parentheses, and it takes a couple inputs. So you saw previously when we were using print, you literally just typed the variable name. Some functions will have keywords so that you to tell it which input it is that you're providing, which lets me sort of shuffle around the inputs in order, and it'll always pull the correct ones. So this keyword for this input is fname, short for file name. And so you'll say fname equals, and then the name of the file. In our case, our CSV files are named like this. And so the name of a file is a string. So we're going to put those quotation marks. You can put single or double. In this case, it doesn't matter which kind of quotation marks you use. And then a comma, so we can put in a second input option, and we're going to call it delimiter. So this tells numpy.loadText, how is your data divided up in the text file you're providing me? Does it have comma? Is it comma separated values? Is it tab separated values? Is it space separated values? That's what the delimiter is for load text. In our case, if we were to open up, one of these files, you can see it's comma separated. Just a comma, not a comma and a space, just a comma. So in our little delimiter, we're going to put just the comma. Also a string. And you can see that it actually gets pretty mad at me. Again, this is an error message and what an error message in Python looks like. You can see this one is much longer than the previous one, right? It has like, I don't know, 30 lines in it. Python error messages can be obnoxious like this because it's giving you as much information as it possibly can. And so whenever you get big walls of error messages like this, the most important parts are like the first 3 lines and the last 3 lines. Because what it's doing, it's called a traceback, where it goes backwards through every function that has been called in the background to trace all of the way back to where the error originated. So in a complicated library that has functions that depend on functions that depend on functions, you're going to get really long tracebacks. But for us, we only need the like first couple lines and the last couple lines. So we can see it's a file not found error. All right, but I think that we learned what the issue is. It couldn't find the file, right? But we can take a little bit of a closer look, just see if we can find out any extra information. It threw the error on the numpy.load text, so that was the thing that it didn't like. And if we go all of the way down to the bottom, even better, it's actually given us an error message. So it says, okay, it couldn't find the file we asked it to find. We asked it to find. And that's because if we go back, we are calling our code from this directory. There's no file in this directory called inflammation. You know, it doesn't know what you're asking it to do. It can't find the file because it's not in this directory. Of course, we've put it under this data directory, right? So all we have to do is go back and add that extra little data with the slash. Just like on like a Windows machine, if you ever use the File Explorer, you'll see the files divided by these slashes for all the directories. That's what this does as well. So it says in the data directory, there's the file called inflammation that you expect to see. And you can see that it has loaded it up for us. If you were running this with a little asterisk, if you were running this somewhere outside of Jupyter, it would not automatically always print this array to screen like this. That's a feature of Jupyter. So normally you would have to put the print function around this call in order to look at the array. Jupyter Notebook is sort of helpful. It's trying to be helpful by printing it to screen for you. Well, you can see it's loaded it up. There's some big matrix tabular data thing in here. Great, we found it. We finally found the data. Another little note on imports that you will see all over code, especially Python code, is importing a library under a different name, which is generally useful, but can sometimes be extremely confusing if the thing you've put after as doesn't actually match the library name, which happens sometimes. You could do. I could call this import as blah, blah, blah. And then I could call load text as blah, blah, dot load text. So if you ever expect to see a library and it's not showing up, head up to the imports. Maybe they've called it something else. The common one is to call numpy np. You'll see this throughout code. It's very, very common. It's basically standard. Because people who code don't like to type the 5 letters numpy and would much rather type np. That's literally the only reason. And so you can see if instead I say np.loadText, I'll get the same thing. But in this case, I'm going to save it. So everybody online and in the room, if you want to take this load text call and assign it to a variable so we can use it later. Because otherwise, when we load an array like this, but we never assign it to a variable, it doesn't get stored. So you've loaded it once and it's not assigned to anything and it disappears. So I will assign it to data. And then if we print that variable, you should see much like what we saw before, some sort of array here. And what type of data do we expect our variable to be? Yeah, so inside of our array here, it's full of decimals. But if we print, oops, wow, can't type, print type data, the variable itself is the data type NumPy array. Because your NumPy array is full of floats. So sort of the external type of the whole array is a NumPy array, and the internal type of the data inside are floats. So we can see that if we do something like this. NumPy array is its own data type, and it's different from a built-in Python list or a built-in Python array. Although they functionally do very similar things, NumPy provides some additional functions that you can do on NumPy arrays to make data analysis faster. So for example, one of the things that NumPy provides is that their NumPy arrays have the property, which is what you do when you put a period after a data class, D type. And that will tell you what the type of data is inside of the NumPy array. So a NumPy array dot D type will tell you what's inside. So in this case, it's full of floats. And it tells you that. Now we might, of course, want to know other information about our array. These little previews very often will use the ellipses to be like, there's a lot of extra stuff here that I'm not printing to screen because it's obnoxious or it'll be too big or too long or whatever. So we can use the NumPy array property shape to give us information. So if we do whatever you've called your variable dot shape, that gives you the shape of the matrix or of the array. So we know that it tells us here that it is 60 by 40. In our case, we have 60 patients and 40 days. And we know that patients are stored in the rows. So we know that this is telling us that it has 60 rows and 40 columns. And that is a pretty Python standard, especially NumPy standard here, is that it will generally give you information in terms of X, Y, or rows columns. So let's take a closer look. I'm going to just do this really quick so we have something that we can actually work with. So we have a little bit of this array, the first 3 rows and first 4 or 5 columns. How do we access it? So NumPy arrays and Python lists and Python arrays are all accessed in basically the same way. You take whatever array you have, in this case I've called it limited data just so we can look at it, and you use these square brackets. So the square brackets differentiate it from function calls, which are the round parentheses. And we know that this is 2D data. It's an X and a Y. So we have to provide it with 2 things here, a row and a column choice. So if we wanted to get just the very first entry here, does anybody know how we would fetch it?
There's a function called fetch.
I wish that would be nice. So the way that you fetch entries is by providing the row and column location of the entry for 2D data. If it were just a row, then you would only have to provide the column entry. If it were just a column, you'd only have to provide the row entry. But because we have both, we have to sort of give it the location and X and Y battleship style of where to find the entry that we're looking for. So this little graphic that I've included in the slides is a really nice way of demonstrating this. So if we have, A, B, C, D, E, F, G, H, I, Python is unique in that the first entry is index 0. So Python starts counting from 0 and goes up from there. And that is a very common bug in Python code, is trying to start counting indices from 1 instead of 0. So always double check that you're starting counting at 0 when you're talking about indices or indexes or the location of data in arrays. So in our case, if we wanted this top left one, you're going to want 0, 0, right? Or well, row 0, column 0 to get A. But if we wanted H, for example, we do row 2, column 1. So 2, 1 would give us H. So we can do that with this data as well. If we want that top left corner, this one, then we do row 0, column 0, and it'll spit out that variable for us. So you can do a little check for yourself. Let's say we wanted, let's do this entry. See if you're able to fetch that for yourself. Was anybody successful? Yeah, thumbs up. Did we get any thumbs up from online? No thumbs up from online. They've all disappeared. If you're having troubles, feel free to just take off your mic to ask a question, or you can drop it in the chat. Hopefully this should be row 2, 0. So, okay, column 0, 1, 2, 3, 4, right? So not column 5. Ooh, and I did a mistake myself. Row 0, row 1, because we start counting from 1. You see, I've been doing this for years, and it's still so easy to fall into that trap.
Can you explain why, when you're trying to get like these individual all variables out, is you're doing the not parentheses but
Brackets?
yes, yeah.
Yeah, so that's because you use brackets to access arrays. So a limited data isn't a function, it's an array. So in order to access elements, they're called elements of an array, you have to use the brackets.
Okay.
If we were doing a function call, that's when you would use the round ones. Yeah. And we'll see that in a little bit. Now, the other thing we can do here is use colons. So we can use colons in our calls to fetch multiple pieces at once. So for example, if I wanted both of these numbers, I would do row 0 because they're both in row 0. But indices 1 as 0 and 1. Oops. Maybe not. Oh, right. There we go. Because the colon goes from the first index to the last index minus 1, which is a pain in the butt, but it's true. So it goes to the first index to the last index, not including, is the way that is phrased often in like textbooks and stuff like that. But it really just means the first index you provide it to the last index minus 1. So 0 to 2 is actually 0 up to 2, but not including 2. So it's going to give us the first and second index. And if you just want the whole of whatever it is, so in this case, if we wanted the entire row, we want row 0 and all of the columns, then you can just, oops, sorry, hit the tab button there. You can just use a colon by itself. So row 0 and every column across row 0. And we can do the same thing if we wanted like the first column, right? And you can also do similar things. So if you wanted the first, everything up to, let's do the third index, we could do something like this. And if you leave either side of the colon blank, it's going to fetch either everything before or everything after. Which is why if you just give it a single colon, it fetches both everything before and everything after, which is everything.
What if I want like the 3 last?
Yeah, so you can, that's a very good question that in case anybody didn't hear, he's asking, what if I wanted the last 3? You can use negative numbers. So here we could do like -3 colon. And it would give us everything from index -3 to the end. People use this a lot if you just want the last index is typically where you see it most frequently. It's just using -1. But trickily, when you use negative numbers, because you can't use 0 for both the first and the last index, if you want the last index, notice you use -1 and not -0, right? So when you're counting from the end of something, you go 1, 2, 3, 4 instead of 0, 1, 2, 3, 4. All of the lovely quirks here. Yeah, so Joseph, you put in the comment that it said it was np.float 64 too, which is also perfectly correct. It's just also giving you the type of that number instead of just the number itself. Yeah. So it's a float 64, so it's just telling you that. Okay, so now we can sort of pick and choose a couple pieces of this data. The reason people love NumPy really so much is because it has a ton of built-in functions for analyzing data. So for example, we can use mean, np.mean, and it'll give you the mean of whatever you provide it. So in our case, if we provide the entire data set, it can give you the mean of the data set across all patients on all days, right? Because we're just feeding it every single thing in this array. Which is great. So again, we're not going to cover everything that NumPy has to offer because it is a lot. So I highly encourage you to take a look at the NumPy documentation or look at a Stack Overflow response if you're looking for something specific. NumPy has 500,000 functions and really lovely documentation to support all of it. So for example, we can, let's take a little bit of extra information. Like we're trying to analyze this data, right? So we can take the maximum of the data, the minimum of the data, and let's even take the standard deviation, STD. This is a fun thing that you can do, which is why I've included it here, where you can assign multiple variables to multiple things on the other side at once by using commas. So max val here is the first entry before the comma, so it gets assigned to the first entry before the comma on the right. So
I have one question.
yeah.
You had NP for NumPy, but then if I didn't already define that, I have to type in NumPy every single time?
Yep.
Okay, got it.
Which is why programmers frequently will call it NP.
Got it.
But you can always change that if you want by just typing import NumPy as NP.
Got it.
Yep. Right, so the thing before the comma will get assigned to the thing before the comma on the right, and the thing in the middle gets assigned to the middle. and the thing on the right will get assigned to the right. Sometimes people will do this to save space in code, or if it's a function on the right that outputs three things, sometimes you might want to assign each of those three things to its own variable. So people will, you'll see that happen sometimes as well. But in this case, this is pretty easy to follow, you know, max to max, min to min, standard to standard. And we can print all of them out. In this case, I'm showing how print statements can be useful by including a string and then a number or a variable. So print statements can be used in this way to provide information to the person running your code if you'd like. So now you can see it actually prints out kind of nicely. The maximum inflation is 20 and the minimum inflation is 0. And so this is a nice way when you're debugging code to send messages to yourself if you want. I do that all the time. Or maybe you're trying to give information to the user as they go along. You can put print statements in there like this that combine variables with standard strings. You can actually see all of the way up here that even NumPy is doing it in this error message. They're including a variable and a string to provide this information not found error message to us. So it's a pretty common thing to do. So now the big thing, if we wanted to pull the maximum inflammation across all 40 days, but only for our first patient. You know, we don't want Nancy and Joe. We just want Bob's information, who gets our first patient. How would we pull that?
The first row.
Right, exactly, right? Because our patients are in the first row. So how do we get just the first row out of our matrix or array?
0, colon, just leave it blank.
Yep, because that's row 0 and all of the columns in it. And now we want the maximum of that.
Max val.
So max val is the
no, wait. You
yeah.
want the standard.
Yeah.
You put NP max and then you just put data
Yep.
bracket. Bracket?
Yeah, so data, because it's an array, needs the brackets, and np.max is a function, so it needs the parentheses. Of course, there's no way to check this. You're just going to have to take my word on it. Otherwise, I believe that Python also has a built-in max. So you don't have to use NumPy's version, but NumPy is, in theory, optimized to work on NumPy arrays. So if this were an extremely large array, np.max would in theory be more efficient and faster than the standard Python library. So then we can actually do something interesting with that. I'm going to actually assign it to a variable so we can use it for later. And then I'll actually print it out. In this case, in theory, we would hope that our data is de-identified and we don't have patients' names and personal information in our database, right? So I'm just going to call them patient 0. And I can print out a nice little message there. So similarly, how would we get the standard deviation for patients across all patients, but just for day 5? We're going to take our array, right?
Colon, comma, 4?
Yeah, right. Because we want all of the rows, so all of the patients, and then we want the 5th day, but we have to start counting from 0. So it's actually entry number 4. Oops. You can see it spit it out for us, but we want the standard deviation, right? So we're going to take that NumPy standard deviation. function. Cool. So I'm going to stop here. It seems like a natural stopping point. See if there are any questions before we really get into the thick of things. Okay, I'm not seeing anything from the chat. Everybody here looks happy. That thumbs up. Feel free to boo me now. No, I'm kidding. Oops. Those 7 variables, and we're going to clear off those. Oops. Cheating, don't look ahead. Okay. So because I started a new Jupyter notebook, I'm going to re-import NumPy. It's a new notebook. It's a new Python script, so it doesn't know about anything we've done in another Python script. So I'll have to redo the import and reload the data. If you're using the same notebook this whole time, you don't need to do this part. But it's simple. We're just pulling NumPy as NP again, and then reassigning our load text of our data to a variable that I'm calling data, which I would suggest you, by the way, do not do in real scripts. Be descriptive with your variable names. Data could mean anything, right? So I suggest if you're actually writing code yourself, maybe I would call this something smart, like inflammation 01, because that's what the file name is called, or something descriptive so that you know, 1,000 lines into your code what the heck data was originally. In this case, we're doing something simple because it's easy to remember for our example. But you will also need to import matplotlib. So matplotlib, math plotting library, matplotlib, is another standard library like NumPy that is wildly, vastly commonly used across scientific computing. There are other libraries that people have started to prefer slightly because a matplotlib can be very unwieldy, but it is a very common one that's extremely well documented. So we're going to talk about it today, and it's really easy to use. What we want specifically is pyplot out of matplotlib. So just like NumPy, matplotlib has a ton of functions. And in this case, pyplot has functions within functions. So we're going to want pyplot. And because now you can really see where that as is going to be useful, because we don't want to type matplotlib.pyplot every single time we want to use it, we're going to import it as plt, plot. This is the common import shorthand for matplotlib.pyplot. You'll see this used really frequently across code. It's just a common scientific Python shorthand. So luckily, pyplot is pretty straightforward to access. They have a function called plot that will plot your data for you. So if I'm calling it a figure here because that's going to be useful later. I'm going to assign this plot of data to the variable figure. And then I'm going to use plt, so pyplot.show, which will show it to your screen. So if you're on a desktop and you type, plt plot data, it won't automatically show it on your screen. You need plt.show to get that pop-up where it'll show the image for you. With the asterisk of plt.show won't work on systems that don't support pop-ups. So for example, the cluster. You can't have a graphical interface pop-up on our cluster. So if you try to do this just raw from the command line, it's not gonna show it to you. And you'll have to save it and then open it some other way. But we can do it here. Great. Wow, what a beautiful plot. It's so legible. Absolutely makes sense. I know what's going on. Absolutely not, right? Who knows what is going on here? It's even difficult to figure out what exactly it's plotting. It goes like 0 to 60 on the bottom, which means that it's probably not days because we only have 40 days. So it's probably patient number because we know we've got 60 patients. but then the y-axis goes 0 to 20, which also isn't the days. So that's probably the inflammation value. And then there's a crap ton of lines. And so maybe each line is a day, but totally not useful, right? So let's narrow it down. Let's just look at the plot for patient 0. We can look at the plot for patient 0 across all days. What's up?
Why don't you, inside the parentheses for plot.show, why don't you have to put big in there?
Yeah, that's a really good question. Functions can have default values that they'll just take if you don't provide anything. Show is one of those functions. I could provide it fig here, and we would know it would plot fig. If you don't give it an option, it will show you the last made figure, which in this case is the plot that we had just made. Yeah. So if I plotted a couple other things though, and then did plt.show, it would only provide me the last thing I plotted.
So at that point, you do have to define it.
Yeah, if you wanted something else, you would have to put the variable of the figure in there. And I didn't put this in here just because it can confuse things. But if we look at the type for figure, it's actually a list, which is a bit odd. But it's holding all of that plotting data. And it's not something you really need to be able to worry about or manipulate for some basic plotting purposes. So let's take our patient 0 and all of the days. We learned how to do this in the last one. You know, it's just 0 with patient across all days, all columns. Okay, something mostly legible this time. So without knowing anything about the way that the matplotlib plot works, you can sort of start to look at this and try and suss out what it's plotting, right? On the x-axis, it goes 0 to 40. So we can probably assume those are our columns because we have got 40 columns, which happen to correspond to us for days. So luckily, naturally, because each day is indexed naturally as the column number, we really don't need to do a lot of manipulation here to get the days plotted on the x-axis, right? It does it for us basically by default. And the y-axis here is we can make an educated guess. That's probably the values inside, so the inflammation values. Because we've only taken patient 0, we know there's not multiple patients being provided here. So, all right. And we can always do a little bit of check here if we wanted to, just to make sure we've got the right information. So data, we were trying to pull patient 0 across all 40 days. If we print the shape of that, it is just a list 40 entries long. So we got the right stuff and we can make the assumption here about the x-axis. So a quick side note here about matplotlib.plot, just because it's a helpful thing. If I made a random X array 1, 2, 3, 4 and a random Y array 4, 5, 6, 7, and then plotted them, we would expect to see, right, 1, 2, 3, 4 here and 4, 5, 6, 7 here, which is what we get. So we can see the x-axis goes 1 to 4 and the y-axis 4 to 7. So you can provide plot with the individual x and y axes if you'd like, just to be super clear. And that's kind of what we did here, although it's a bit of a mess. But you can see when you only provide it something that is one-dimensional, so just the inflammation values in an array 0 to 40, it has by default set the x-axis to the index numbers 0 to 40 because it doesn't know what else to put there for you. And so we can see if I just plot array, like just the X array, that's 1, 2, 3, 4. It by default takes the indices and puts them on the x-axis, which is 0 to 3, right? Index 0, 1, 2, 3, and then has plotted points 1, 2, 3, 4 on the y-axis. So if you just provide it with a one-dimensional array, it's going to use that as the y values and the indices as the x values. And that's the default behavior.
So I just did what you did
Mhm.
on my own, and mine is giving me 2 decimal points versus one. Is there a reason? for that?
2 decimal points on the labels.
Yes.
Not really. It could be like the default settings or something like that. Okay. So just be careful, I guess, is the point when you're using plot to make sure that you provide it the X and Y axes you actually want it to use. Otherwise, it's going to pull some defaults that don't always match what you want. So that's great, but we want to actually make this plot usable. Let's say we want to give it to our PI and be like, look at this great plot that we made. Inflammation peaks on day 20 and it increases and decreases on either side. We don't want to hand it to him like this. He would not know what they were looking at if you handed your PI a plot like this. So we obviously want to add some axes, labels, a title, maybe a legend, and we can do all of that in Matplotlib. So let's add some labels. First, I'm starting, if you'll notice on the x-axis here, because it has pulled the indices, it's going to 0, actually to 39, because those are the index numbers. So you can see it actually doesn't make it all the way to 40. But that actually doesn't make sense with days, right? I mean, maybe you could call it day 0, but if we wanted to call it day 1 to day 40 instead of day 0 to day 39, we'll need to provide it our own x-axis to make sure that those numbers get plotted correctly. And a common way to do that in Python is using the built-in function range. Let me actually delete this so we can do a little bit of fun with range really quick. Range is a built-in Python function like print. It's a function, so we're going to need parentheses. And it will take the first number you provide it up to, but not including the last number that you provided. So if I say 1 to 40, oops, let's see. I'm going to do this just really quick so it'll print correctly. We'll get to this later, don't worry about it. This is a side tangent. It goes 1 to 39 because it's up to but not including the last number. So if we actually wanted 1 to 40, we're going to have to ask it to do 1 to 41. The other fancy thing about range that we're going to cover it later. I'm not going to mention it here. But I just wanted to give you a justification for using it in our plot. So we want range 1 to 41 in order to get the days 1 to 40 on our x-axis. So we're going to provide plot the x-axis first and then the y-axis. So we want the days first, which I've very creatively called x-array, and then our actual patient data. Now, the other important stuff that you're going to want to use are the x labels, the y labels, and the title. Luckily, they're called x label, y label, and title to make it easy to remember. So if you want to add an x label, you do plt dot x label, and then the string for whatever you want that x label to be. Same thing for y label and same thing for title. These labels come with a ridiculously wide variety of options in order to manipulate them. Maybe you want to tilt them 45 degrees. Maybe you want to make them interesting colors or make the text bigger, and or there are so many choices. We're not going to cover that here because there are too many choices. And there are lots of really great tutorials on Matplotlib that already exist on the internet that you can very easily find. So we're just going to cover the basics, get a nice little, I don't know what that is, Calibri maybe, X label, Y label, and title. And just like your question before, it's adding it to the last figure that we've plotted, like with plt.show. So it's adding day information and the title to this last figure that we plotted. But you'll see soon if we plot multiple figures at once, then you have to be a little bit more specific. Great, now we have an actual working plot that we might be able to hand to a PI, especially if we're just doing some like basic analysis. Maybe you'd want to put units on inflammation. I don't know what the units are, so I'm not putting them in, but you probably should. want to plot two patients at once so we can actually start to look at trends across patients, right? And across all days. So we can do plt.plot and provide it with a new input option called label. And that will give whatever line you've asked it to plot a label and a legend later if you need it. So I can do this twice, plot twice on the same figure because I haven't made a new figure yet. And because it will always just reference the most recent figure, it'll put it on the same figure for us. Let me also add, oops, a plt.show here, if that is most proper. And then the key here is that after you've added your labels, you also have to call legend. Otherwise, it will have the labels in its mind, but won't actually show them to you. So it'll have the labels as properties of the figure, but won't actually plot them on the figure. So you can see here, we've got a new figure. Unfortunately, I didn't add the X and Y axes again. And because it's a new figure, it doesn't know that we want the labels or the title, so it's not going to show up here. But we can just do a quick little copy paste, maybe. Oops. Wow, rude. Try again. And get the now we're really cooking, right? We've got two patients on the same plot with a legend even, which is very nice. Depending on your plot, the legend might get in the way. So the legend has this default choice where it'll put it in the upper right-hand corner. Legend also takes a wide variety of inputs. If you would like to move it, change the order, change the color, you can do everything from like changing the background of the box to be transparent, or maybe you want it to be purple in the background, or you want to change the color of the lines. All of these things are possible. And also like changing font sizes and things like that, or moving it to a different place in the figure, or even putting it outside the figure. All of these are possible. This works for us today. So this is great. Now we can see that two patients on the same plot, still mostly legible. And you can sort of see that there seems to be a common trend here. You know, we start low, we end low, and there's a peak in the middle. Now we know from previous experience that if we tried to put all 60 patients on this plot at once, it would be a nightmare, right? We end up with this gobbledygook, which is not helpful for anybody. So matplotlib supports a wide variety of plots: scatter plots, box plots, whisker plots, bar plots, pie charts, whatever your heart desires. It probably already exists in matplotlib under a function. So here, what I think would be useful with so many patients is probably like a heat map, right? Something that could display all of the patients at once and be clear on where the peaks are. That's where my head was at. You could choose something else. I think a heat map is going to be the easiest with so many entries. So in matplotlib, the call for a heat map is called IMShow. I'm not sure why, to be honest. That is not an intuitive name to me, but that is what the matplotlib name is. Usually the other plot names are straightforward. So if you wanted like a scatter plot with points, it's plt.scatter. Or if you wanted a bar plot, it's plt.bar or plt.histogram. You know, they're all very normally named reasonably, but for whatever reason, the heat map is called IMShow. And I put a couple note about that. Yeah, sort of little comments about this in here for later if you want to take a second look. So you can see pretty straight, like with 3 lines, we've got a really reasonable heat map here, which is the magic of matplotlib. Matplotlib does support putting heat bar legends in there so you can actually see the values of the colors. It's a little bit more complex, so we're not going to talk about it. It's a little annoying. But this at least gives us an idea of the trends, right? So we can see across all patients, 0 to 60, they all have this peak around day 20, and they all go 0 to 0 on either side. So there's a pretty clear trend in our inflammation data across all days, which is nice. That's good information to know out of 3 lines of code, right? So we can get a little fancier. Maybe we want to look at statistics of the entire data set and make some nice plots of those. Because we're sort of eyeballing this really nice heat map, but that's not scientific. So let's try to do something a little bit better here. We can take, for example, the average, right? It's the mean. And in this case, let me actually, we'll type this in here. So before we were using numpy.mean, mean, and then the data, right? And this is giving us a single value, which is the mean for the entire data set. These kinds of NumPy functions will also support doing whatever it is that you're trying to do, like the maximum, the minimum, or the mean, or whatever, over a specific axis, which means either over like each column or each row. And that's under the axis keyword. So in this case, if we provide it this axis keyword, it's going to do it over axis 0, which I believe is per patient. I have to double check because sometimes the axes get backwards, but in my head. Oops, we actually don't need that. But so by taking it over axis 0, it is doing it per patient. Good. Okay. So it's doing it per row. And axis 1 would be the column. And if you had 3D data, then axis 2 would be the Z, right? So X, Y, Z, axis 0 is the row, axis 1 is the column, axis 3 would be. So now we can plot this average of each patient over all days, right? And now we sort of have an actual statistic of what we eyeballed in this plot, that the average for each patient does actually peak on day 20. And, maybe we also want the minimum and the maximum. You could do a very, very similar thing, right? And again, over axis 0, so per patient. I've added labels here because we're putting it on the same plot. And the legend. And in this case, because we've only got sort of 3 lines, we might be able to put all of these on the same plot together and have it still be legible. But just for tutorial's sake, what if we didn't want to put them on the same plot and we instead wanted to put them on 3 separate plots? But our PI is terrible at data management, and so they all need to be in the same figure or else they're going to lose them. We can do that too. So this is the case where establishing that figure is going to become important. So we're actually going to make a figure object in this case by using plt.figure. And by using plt.figure, before it was, if you call plt.plot without calling a figure, it's just going to pull all the default options in for you. But by establishing plt.figure here, we can make it an object and actually define some of its properties. So, for example, one of the properties you can give it is the size. And so you can see now this object fig, instead of being a list, is actually a figure object, like a figure data type. And it tells us that it's 1000 by 300 pixels, but nothing is plotted on it yet. So it calls that 0 axes. And you don't have to provide it a fig size here. It'll pull some default value if you don't provide it a fig size. I just wanted to show that you could do that. So this is the plotting bit that gets a little bit complicated, so please feel free to stop me. But this is a very common use case, so I wanted to make sure that we covered it. If we want to add subplots to our figure, there's a function for that. You take whatever you called your figure and call add subplot. It is convention in Python to call each of these subplots an axis and label them 1, 2, 3, 4, or whatever. So that's why you see I'm calling it AX1 here. And the options that subplot takes is the, let me make sure I say this right. The, oh geez, I never remember what the 1, 2, 3, because there's 3 dimensions, but we only have 1 row. So oh geez, I'm not going to remember now. I should have put a note in. Hang on. Give me 1 sec. Make sure I tell you the right thing here. This is a great example. Luckily, because these are common libraries, a simple Google search will get you most of the answers you're looking for, because the documentation is so good. Okay, good. I was right. All right. So it goes row, column, index, right? For the, what did they call it? I guess they call it a position, I think is what they call this whole set. And it's always the 3 numbers, row, column, index. So we can add that subplot and then take a look at Fig. And it has 1 plot in it. So we can do it again, increasing the index each time. And now we've got 3. And of curiosity, I think. Let's reinstantiate this. Do this. I do. I think that's probably a typo. That's what I thought. Just making sure. I'm just fixing this really big. There we go. Beautiful. So the way that it works here is that we're asking to add a subplot that has 1 row and 3 columns, and we're putting this specific subset of that subplot in index 1. Notice index now counts from 1. Annoying, I know. But for matplotlib, the indexes start at 1 and increase from there instead of 0. So we've gotten a figure that is 1 row. There's maybe 2 other invisible columns here that we can't see. And we've only put this in index 1. So you can see better once you add the other 2 subplots here that there are actually 3 columns and that they've each fallen in index 1, 2, and 3. But only 1 row. So if we changed this instead and did 3, 1 instead of 1, 3, then it would be 3 rows, but only 1 column. So they would be stacked vertically.
So the indices start at 1. Is that what you said?
Yeah, and matplotlib, unfortunately, the indices start in 1, not 0, just to make it as confusing as possible.
But you would get an error message if you started at 0.
Yeah, it would yell at you. Okay, so let's actually put some data on this. We've called each plot individually, AX1, AX2, and AX3, and we're going to need those variables now so that we can actually add data to each of these subplots. So instead of saying plt.plot, which was, remember by default, just calling the last figure we had made, we actually have to put them on specific plots. So if we want to put the mean on this first plot here, then we have to call AX1, which was the subplot, and plot it there. Oops. I'm not going to do that. What happened? And I'm also going to give this subplot a Y label, so in order to differentiate it from the other subplots. So I'll call this one average because we're plotting the mean. And then I can put things on the other two subplots as well. So I'm going to make plot 2 another plot of the maximum, and I'm going to give it a Y label. And then I'll do the same thing for our third plot, axis 3. But in this case, I want to make a scatter plot instead of a plot with lines. So I'll call ax3.scatter and give it a slightly different input for the minimum data, and then I'll still give it the Y label. And here I can actually oops. I will copy paste one of these little blurbs into chat here in case you want to copy paste as well. Because it's a repeat code over and over and over again. And we can take a look at that. So great, by default here, maybe I can make this bigger. Yeah, nice, okay. By default here, we've got our 3 plots, just as we expect. They look the way that we expect them to. And you can see here what matplotlib.plot has been doing by filling in, the line values. So before we got this step plot, but actually the data is these discrete points, which if you connected them would look like that step plot. So you can see that matplotlib has literally just been filling the line in between each of the decimal points, each of the plotting points. And again, each of these subplots has a ton of different things you could change about it, but we can see immediately that our Y labels are overlapping sometimes with the plots between it. Matplotlib does have a couple built-in functions to automatically fix these things, with the asterisk that the automatic fix does not always work. In our case, it will, because it's a simple issue. So I like fig.tight layout. And it's basically a catch-all to fix some basic problems like the labels overlapping with the boxes. And it also makes sure that it fills out the entire space in pixels that you've given it. So you can see it also got a little fatter than the previous one. There are a couple different layout types that you can choose from. I personally like tight layout because it cuts all the white space from the top and the sides. Yeah.
So when you were specifying the big dimensions, that was way back when, that was in pixels?
Yeah, so it sort of interprets it into pixels. So it's usually the number you provide times 10 in pixels. Yeah.
So it's not like centimeters or inches.
You can, by providing some extra input options, you can ask it to let you define it in inches or centimeters or whatever if you are trying to make like a nice PDF or something. That's a specification you can make here under fig size. Yeah.
Axes, it looks like they're not spaced correctly.
What do you mean?
Like going from 0.2 to 0.2 to 0.4, like the describe it. They're kind of like on top of each other. You can see. Like, because clearly the axis is it.
Oh, yeah. Yeah, so this is one of the examples that I'm talking about. It looks like it's taken your data and put floating points on the X and Y axes. It has a hard time with floating points sometimes and getting the axes to arrange themselves correctly. It might also be because the figure size you specified might be too small to fit the drawing in it.
Okay.
So in which case it can sometimes squish the X or Y axes and you end up with these weird overlapping labels. And that's where all of the additional options in Matplotlib come in.
Gotcha.
A common way to fix this is by tilting your X-axis labels and making them 45 degrees.
Okay.
So you could put like long names or something there so they don't overlap. And this is also a good example of when tight layout doesn't always work. It tries to fix it automatically and kind of ends up a little screwy. Another thing that I'll mention here that you might want to do, especially in a chart like this, where you're plotting the same kind of data across all three charts, the y-axis doesn't match, right? It goes 0 to 5 on one place, 0 to 20 on another, 0 to, I don't know, 16, maybe 14 on the other one. You can set global minimums and maximums on your plots. And you can sort of specify the range that you want to see plotted on your X and Y axes. You can make them log-based, natural log-based. All of these are matplotlib functions that you can add. And the other thing we can also do is add a title. You could do fig.title and add a title to this that would span across all three of your axes. And the final thing that you definitely want is save fig. So you can save your figure. In this case, if you don't provide a .png or .jpeg, it chooses some default. I think the default is PNG. But if you specify in your file name that you want to call it .jpeg or .png, it'll follow the specification that you've asked it for. So like maybe I want to call it inflammation.png. Then I can come here and see that it is now saved in that same directory on our cluster. You can also be smart and maybe put it in with your data and just add the folder. And then we can see it shows up there as well. I highly encourage you to take a data set of your own that you know what it looks like and mess around with it in matplotlib as a way to just teach yourself and learn for yourself what all the options are. Because like I said, there are a million of them, which is one of the reasons people actually don't like matplotlib is because there's sometimes too many options that it gets complicated to figure out exactly like which inputs you need to be providing to manipulate the plot in like just the right way. Do you have any questions about matplotlib? We can pull up some functions pretty simply if you would like to, if you wanted to like see what changing the y-axis looked like or anything like that.
How do you have a title to the whole thing? I tried to click that.
Yeah, let me see. Is it fig.title?
I tried that and I didn't like it. I was like, that doesn't exist.
Ah, you're right. Okay, hang on. Let me see. And it might be set title. Because I think if we do ax.set title, I think that will give, oops, ax1, sorry. Yeah, that'll give an individual title to each of our axes. So can we do, let's see. And see, this is what I mean by matplotlib having too many options. Oops, it's not. Oh, yeah, we need to call it something. No. Oh, it made a new figure. Okay. Yeah. So hang on, let me see if I can remember or look up really quickly which set the title.
Soup title.
Oh, soup title. You might be right. For super title. Yeah.
Except mine doesn't sit right.
There we go. It's kind of hard to tell because I've used tight layout, so it sort of smushed it together.
Yeah.
But this is actually centered over the entire plot and not over this center one there.
If you wanted to untight layout your plot,
Mhm.
how do you regenerate it without that? Because it seems like it'll.
Yeah, so because we're in Jupyter, where it saves everything before it,
Mhm.
you would have to go back and run the previous cells again to regenerate it. Normally in a typical Python script, you would just delete that line and run the Python script again, right? Yeah. You can also manually set all of the layout options. And if you put any of those after tight layout, then it'll overwrite the tight layout options because it's become later. And a lot of, just as a quick example, a lot of these will take other options like this, like the size of the titles or the font or the color or anything like that. You can get really, really detailed. Like scatter plots, for example, you can change the size, color, and shape of each of the points on there. They can be hollow, they can be circles, they can be stars, they can be yellow, rainbow, pick your poison. The world is really your oyster with Matplotlib. Okay, well, we're coming up on noon anyway. So feel free to ask me questions. Until then, people online, all right, welcome back. We are going to work today, this afternoon, on everything that we need to learn to do some basic for loops and some basic if else statements so that you can start incorporating some logic into your Python code. So starting out with lists. Lists are very similar to arrays. They typically are only one-dimensional though, so like just a single row or something like that. But they are their own Python class. And because they're built into Python, you can just make one without having to load a library. And you can make a list by, oops, I got the caps lock on. There you go. You can make a list by literally sort of typing it out with the brackets like this and putting all the numbers in between and sort of doing it manually that way. You can also use like list as a function basically and put stuff inside. And just like NumPy arrays, you can put basically whatever you want in here. They can be numbers, strings, floating. You make lists of lists even, which is a dangerous thing to do, but you can do it. So you can see their own sort of data type in Python. And they're indexed just like you would index our arrays, our NumPy arrays. So everything that we learned already about finding and fetching data out of NumPy arrays holds for lists. You can do the same brackets with the same index numbers, and the colon trick works, the -1 trick works. It's basically just the same as a NumPy array. And you can, as I mentioned, put even different types of data together in the same list. Although I would not do that if I were you. It makes using them practically pretty difficult, but they can. So lists, similar to arrays, you can replace values of by assigning the index of that value to something new. So like in this case, if I make a list of names, Curie, Darwin, and Turing, except I've got a typo in Darwin, it's Darwing, and we want to change that back. How do we fetch Darwing out of names? Just one, right? Because it's just one-dimensional, so it's even simpler than the array we were dealing with before. And we can just set that equal to something new. So I want to fix it to be Darwin. and it has changed the value of that index to something new. So it's gotten rid of Darwin and it's replaced it with Darwin, which is what we wanted. You can do the same thing in arrays. If like we had taken that NumPy array and decided we didn't want the first index, the first thing in the first index to be 0 anymore, we could have set it to something new. But you'll note that if I had instead, back up and run this, so that name's back to Darwin. If I instead just wanted to fix Darwin and capitalize the first letter, I couldn't have done this to replace the lowercase with the capital. Because strings won't let you index them in this way. So you would have to wholesale replace the entire string. And that's what I was getting at here. Same thing, right? So there are two kinds of data in Python. The fancy computer science term for them are mutable and immutable. Mutable data are things that you can be modified in place, like our lists or arrays. And immutable data are data that can't be modified in place, like strings. And tuples, which will come up later. So, just like arrays, which we actually didn't talk about, which is why we're covering it now, you can add data to arrays and lists. You can pop data off. You can do all kinds of things with them. So let's say, I wanted to put the next prime number in this list or odd number in, prime number in this list. You can use just dot append to add something new to the end. And NumPy has a very similar function. It's just called np.append to add things to the ends of NumPy arrays. Or we could, decide actually we don't want that one in the front and we can pop it off. So append and pop are the two pretty easy, two most straightforward ways of manipulating lists. Append will always append to the end, and it'll append to the thing that you put in the parentheses. So in this case, we said number 11. And pop will pop off the index that you specify. So we said index 0, so it took off the 1 at the front, but we could have put in any index there. And again, there are tons of other things you can do with lists and NumPy arrays. These are the most simple ones that you'll probably run into the most often, popping and appending. And then just a side note here about lists and variables and how you reference items in a list and how you reference lists. So if I make a list of the ingredients to my salsa, and let's say I put peppers, onions, cilantro, and tomatoes in it, this is like a generic recipe for salsa. And then maybe I have my own special recipe for salsa. So I'm just going to say my salsa equals salsa and print them both out. So they have the same ingredients in them right now because I've said my salsa equals salsa. So they're the same list. But then if I change the first ingredient in the generic salsa list, I would hope that my salsa doesn't also get changed because I want it to be separate. But in this case, my salsa is also changed. Because unlike what we saw previously with variables, when you set a list equal to another list, and this is also true of most arrays, it's actually just a reference to that list. So instead of making a copy of salsa, when you say my salsa equals salsa, it hasn't made a copy of the original list. It just says, oh, whenever you call my salsa, actually point to salsa instead. So it's not made a copy of the original salsa. It's just a pointer. It's like, oh, you said my salsa. Well, salsa's over there. That's the one that you want. So if you change the reference salsa to something new, and then you ask for my salsa, it's going to be like, well, that's salsa, and you changed salsa, so I'm also changed. It's a bit of a weird quirk of list assignment like that. Does anybody have any questions?
Is that for all types of variables or just for list?
So it's true for lists and arrays.
Okay.
Like we sort of saw before, it's not always true for basic number variables. The way to get around this is by actually making a copy of the original list so that if you change the original list, it wouldn't change your copy of the list. So you can do that by actually instantiating a new list by adding the list call around salsa. And then because my salsa is a copy of the original and not a pointer or like a reference to the original, when you change the original salsa, my salsa is not also changed. And the only reason I bring this up is because it can come back to bite you, especially in for loops. If you're doing something to a list in a for loop and also using that list to generate the for loop, you can accidentally get caught in a weird catch-22 there. When you make, oh, let's change this note here. Copy. When you make a copy like this, it does require new memory. So sometimes people will make these references because they don't want to make a full copy of the original list because they're trying to save memory. But when you make a copy, you are also duplicating that amount of memory. So if it took like 10 megabytes of your original list, whenever you make a copy, now you've got 20 megabytes hanging around instead of referencing, which doesn't take up any additional space. Which is only really important once you really start getting into the weeds. Right. So this is another example of how this can sort of get you into trouble because we have made primes a reference, not a copy, a reference to the original odds. If we append something to primes, it also appends it to odds because they're the same list. So because they're basically references to the same exact list, if you manipulate one, you manipulate both. Whereas if we had made primes a copy of odds, then this wouldn't happen. Okay. With that little caveat in mind, we can do some fun stuff with lists. So if we have our two different lists of different lengths, we can maybe think naively about adding them together and hope that if we add 11 and 13 to 1, 3, 5, 7, maybe we'll like do 1 plus 11 plus 13 or something. But that isn't how lists work. So the basic addition, subtraction, multiplication functions on single numbers don't always work the way you expect them to on lists. So if I try to add 1, 3, 5, 7 and 11 and 13 together with the plus sign, what I'm actually going to get is just a single list with all of those indices in it now, because it's just taken 11 and 13 and appended it to the end of the previous list. So be careful when you're trying to, like, let's say you wanted to add the number 11 to every single item in odd nums. You can't just do plus and then a list with 11 in it because it's not going to do what you want it to. And maybe if we want to add, if we're trying to get to this goal of adding 11 to every item in the list, we think we're being smart and we're like, well, we can just do plus 11, the number 11, instead of a list with 11 in it. And maybe that will work. But that also doesn't work with lists. Python will throw an error because the plus sign to Python means append or concatenate these two things. And when one of them is an integer and one of them is a list, it's not able to do that. So I think I talk about it later. Yeah, okay, good. So multiplication, same thing, also doesn't work the way that you think it will. instead of multiplying each individual number by 2 here, it's just going to multiply the list itself twice, meaning it's going to take the original list and make a copy of it and then concatenate them together, sort of append the two together. So instead of, 1357, we now have 1357, 1357. And the same thing can happen too if you're trying to take a list or a list and multiply it by something short, it also there's an error because it's technically a sequence and not a list. So you can see how this gets a little hairy. So while these lists are pretty useful, they're basically they can be functionally the same as a 1D array. So a lot of people will instead just use NumPy arrays because NumPy arrays, like these one-dimensional NumPy arrays, actually do work the way that you think that they will naturally. So if we import NumPy again and make the same list, 1357, except instead make it a NumPy array, if we try to add 2, it does what you expect it to, and it takes 2 and adds it to each individual index. And so this is that special behavior that changes a NumPy array versus the standard list, is that it handles these sort of mathematical operations differently than the standard Python list type. And so we can do the same thing with multiplication. Like now, let's say I want to multiply every index by 2. It does what you think that it does. Multiplies every index by 2 instead of duplicating the list twice. And it can now handle the same kind of multiplication if you give it a single item, like a single item list. It'll also do sort of what you expect. And you can also get a little bit more complicated with this. Like, let's say I want to take this array and multiply the first index by 100 and every index after it by 1. It will do index to index multiplication. So if you have 2 NumPy arrays that are the same size and you multiply them together and with the asterisk, it will take the first index of each and multiply those together, the second index of each and multiply those together. But if you're trying to do this with NumPy arrays, they do have to be the same size. If you try to multiply 2 arrays of different sizes together, that's when NumPy doesn't know what to do anymore. Because it's like, I can't multiply index by index because there's more indexes in one of these than the other. And so that's when you'll get an error about them not being the same shape. This is one that comes up a lot. Especially when you're doing some sort of basic data analysis, if you accidentally end up with 2 sets of data that aren't the same size and you're trying to multiply them together, you'll run into this broadcast error pretty frequently. So this is sort of a warning to make sure whenever you're coding that you're sure that the data that you're handling is either a type Python list or a type Python NumPy array, because they behave differently, but they look the same. And all of the sort of fancy properties that you get with NumPy arrays as well, like np.max, dtype, shape, all of that is unique to NumPy arrays, and you don't have the same properties necessarily with Python lists.
Question.
Yeah.
If this was like real data and you were trying to like do something with it and you had missing data, what's the best, is like NA, or what's the best way to represent that so it doesn't like break your whole business?
Yeah, that's actually a really good question. So Python does technically have a type of nan, like none is a choice in Python. You can see it's highlighted like a true false sort of thing. And so it totally depends on your data what the appropriate fill value is in this case. Sometimes filling 0 in is the right choice, but sometimes a 0 is actually meaningful, in which case you probably want to fill it in with something like none. Yeah. And so if you're trying to load in, for example, a blank in like an Excel file, most functions will have an option for you to choose how it wants to handle blank cells. Like, do you want it to be loaded in as a 0 or a nan or none, or so usually that's an additional option.
Okay.
It comes up most often reading in Excel files when you could have blank cells.
Yeah.
Yeah. But yeah, none. None is probably what you're looking for. Because it doesn't have like if you do type, for example. Oh, oops, hang on. There we go. None type is a type in Python. Yeah. That's distinct from like an integer 0 or a true false.
Okay. So
Yeah.
you can put it with like a list of numbers and that's not gonna upset anything.
Yeah. So things like NumPy know how that if you take a NumPy array and it has some nuns in there as well, it's generally smart enough to know how to handle that. Or throw an error at you and let you know. Great. Okay. So if we have our list here and we just want to prompt, we just want to print each number in this list. I mean, I think that we could all sort of come up with something like this, where you just print each index, right, in the list like this, which is perfectly fine for short lists, but quickly becomes a problem if your list is longer than like, I don't know, 4 indices, right? It gets pretty annoying. And if we decide to pop off the end, so like if originally my code said print the 4 indices because there are 4 indices, and then at some point we change the length of the list by popping off the 7 at the end, then this is going to error out because now we're looking for an index that doesn't exist anymore, right? And this is where for loops really shine. So if you have some data like 1357, and you want to print every number in the list, use a for loop. So the anatomy of a for loop is basically for this thing in this collection, do a thing. So if we want to print every number in the list, we could say for number in the collection, which is our list, odds, and then a colon. The colon is important. That's important Python syntax. You're going to hit enter. And then for loops in Python, the way that the structure works, anything indented with 1 or 2 indent, well, with the same indent, I'll say. It's an argument ongoing whether or not to use 1 or 2 indents. But let's say it's 1. Anything under here will happen for every single loop. And if you ever break this indentation by putting something like this at the end, then this will happen after the for loop is over. So the way that for loops are defined in Python is solely through indentation. Some programming languages will use brackets and things like that. I think R does that. But not Python. Python relies on indentation.
So if you wanted to have like a loop in your loop, you just
Keep indenting it. So we could do that. We could do the same loop again if you really wanted to. Nothing is stopping you from doing this, and then you could print again. And that's a loop in a loop. So anything past this indentation will happen for every loop at the top, and anything past this indentation will happen for every of that loop, second inside loop. But so if we just do something simple like this, you can see it prints 1357 and then the end at the end, even though it's not in our list because it happens after the for loop. And the benefit of something like this is that it doesn't actually depend on the hard-coded lengths of our array or anything like that. So if we pop something off the end and then run it, it doesn't actually throw that error because we haven't hard-coded an index value or something like that into our code, which is when this is extremely helpful. Yeah.
question. Num.
Mhm.
we haven't defined that, right? What is that?
No, yeah. So that's really cool. That's actually what I was just about to get at. Um, yeah. In the anatomy of the for loop was for thing in collection do a thing. Whatever you call thing doesn't matter. It's a new variable you're defining that will exist within the confines of this for loop. So I could say for blah in odds, print blah, and the same thing will happen. So this thing that you're defining is now a variable within the for loop that you can do with what you wish. And that is equal to the value that you're pulling out of your collection. So in the first go round, it's equal to 1, and the second go round, it's equal to 3, and in the third go round, it's equal to 5. Now, something to keep in mind here is that if we say this variable that we've just defined, blah, is now equal to 3, well, let's say like 1,000 to differentiate it. Let's do this. Print blah, print blah, so we can see what the difference is. And then print odds. And we'll print it at the beginning as well. So odds should have 135 in it at the beginning and the end. But now we've set our variable that was originally pulling the values out of odds to 1,000. We want to make sure that it hasn't changed the odds list to only include 1,000 over and over and over, right? And it doesn't. So in this case, the variable that you defined, blah, is a copy of the value that you're pulling out of odds and not a reference to it. So you're safe to do whatever you want to that variable name without actually changing the original list, which is one of the reasons why it's so useful. The other thing to know is that the variable that you define here as whatever this value is that you're pulling out of odds exists now in your code. So you can use it after the for loop is over as well. And it'll just be set equal to whatever the last thing you had defined it to be as. So in this case, the last thing in odds is 5. And so at the end of the loop, after you've gone through 1, 3, and 5, if you then print it again, it's just going to be 5 because that was the last thing that it was. And you can also choose to do absolutely nothing with the variable that you defined if you just want to sort of use it as a placeholder to loop through the length of odds. So for example, if I just wanted to make a number that increased by 1 every time I went through odds as a sort of brute force way of finding out how long the array odds is, I could do that, right? So I could set some variable outside and then increase it by 1 every single time I looped through a value in odds. So at the end, if odds is 1, 3, 5, 3 long, I should expect length to also be 3 because I'm adding 1 every time we go through. And it does, in fact, give you 3. So in this case, we didn't actually do anything with the variable that we had defined. We were just sort of using it as a dummy placeholder. This does happen sometimes in Python code. And usually if somebody is making a variable like this as a placeholder, they'll just use underscores. They'll just call it underscore 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 because as a way to let you know that it's not going to be used again. Oops, hit a button. Right, and we did that. Right, so If we, in this example, we like when I had set blah to 1,000, like I actually wanted to change every value in my array to 1,000, but that didn't work because blah was a copy of the original. A very common use case in Python is a function called enumerate, which is sort of an extra thing that you can do with lists. So enumerate is a function that returns a tuple, which is just two numbers in parentheses. So we can say tuple like 0, 1. And then if we do type, oops, let's set this to blah. You can see that it's a tuple. A tuple is a pretty frequent thing for functions to return because it's immutable. So you can't change the length of it and you can't change the values inside. So it's a good thing for functions to return because you don't want to be able to change the thing that a function returns by default. So enumerate returns a tuple, which is just the set of two numbers. The first number it returns is the index number, and the second thing is the value at that index in the list. So we would want to do like for, let's call it thing, right? In enumerate odds and print thing. So we expect this to return the index and then the thing at that index as a tuple every single time, which is what we get, right? So we get 0 at the 0th index is the number 1. At the first index is the number 3. The second index is number 5. This is very helpful in for loops because, for example, let's say I wanted to change every single number in odds to 1,000. Now I have the index number during every loop. So I can do something like, oops, hang on, let's do this first. So the common way you'll see enumerate used in a for loop statement is by doing index value. This is that unpacking we were talking about before, where it's returning two things at once. So I'm going to assign each one of those individually to its own variable. So now I have the index under the variable index and the value under the variable value, and I can manipulate them independently. So now I've got the index. I could do odds and then put that index in there, which will be 0 during the first loop, 1 during the second loop, and 2 during the third loop. Say that equals 1,000 every single time. Oops, need that if statement in there. With the B. So now because I'm manipulating the array directly in the loop every single time, I can change each index in the loop to be what I want every single time. Whereas before, when we had set, thing as the variable and tried to set thing to something else, that was a copy of the value. But now if I actually fetch through the array directly using the index, I can actually change those values. So this is useful. You could use this as sort of a blunt force way to do anything to the values in your array, right? You could square all of them or take the natural log of each one and have the array at the end that contains all of the new values. But this does overwrite the original list, so you lose that original data when you do it this way. But sometimes if your data is very large, you don't want two copies of it. You just want the resultant data. So this is that sort of same example. Right, and if you remember I said we were going to talk about the range function again. The range function is also one that comes up a lot in for loops. So we can use it, for example, print the numbers 0 to, but not including 10, right? So 0 to 9. And it'll print all of those out for us. The other thing that the range can do is it does also take a third input if you would like. So usually that third input, the default is the number 1, because the third input tells you how the step size between each number. So if I wanted the numbers 0 to 10 with step size 1, so I want every single number between 0 and 10, it's going to do that. But if I say the step size should be 2, then it's only going to give me the even numbers, because it's jumping from 0, and the step size is 2, 4, 6, 8. And you can make this whatever you want, 100, 300. Of course, if I try that with 0 to 10, it's only going to give me 0, right? Because 100 is outside of the range of 10. And this is used most frequently by fetching the length of a list, which you can do by using the Python function len. So if I just do like len odds, oops. Oh, oods. There we go, we got there eventually. It's 3 long, right? Because it has 1, 2, 3 indices. So len, confusingly, returns the actual length of the list and not the length minus 1, which would be how you would get the index, the last index in the list. So you can see that sort of here, when the length of odds is 3, taking the range 0 to the length is really taking 0 to 3. So it's printing 0, 1, 2. But this is a way to get, for example, the index, all of the possible indexes in odds. It gives you index 0, index 1, and index 2, which are the indexes that exist in odds. Which is boring but useful in the long run. So let's actually do something, unless there are any questions about for loops. It was like a lot of crunchy information, but we'll actually use it right now to give you a real life example. Okay, cool. Yeah.
If len or len some list or like one-dimensional array gives you the number of like items in that array, why would you bother with this for loop? You could just, if it's right there.
Yeah, so sometimes you want the actual index number, which is what this for loop would give you, whereas len just gives you the number of things in the list, but it doesn't actually give you all of the indexes in the list. So this is like a way to generate. It's basically a clunky way of using enumerate. So if we didn't have enumerate, this is the way that you could fetch all of those indexes and do something interesting with them.
Is there any situation where it wouldn't just be 0, 1, 2, 3? Like,
not really. Indexes are always integer numbers, 0 to the length of the list. So really you should probably always be using enumerate. There's no real reason to do something like this, 0 to the length of a list. Unless you didn't need the values in the list and you just wanted the indexes, which is what this would do. So this was basically functionally equivalent to like if we did for num dummy variable. Like this is the same. Because we don't want the second thing that comes out of enumerate. Range is sometimes useful in other ways. People will usually use it to like generate some dummy data really quick to do a test on. Like you could just generate an array of 100 numbers or something like that, The one I also see people use pretty frequently is numpy.random, because that will generate an array of random numbers, which is very useful if you're trying to like test a pipeline or something. And then you can also give it some limits even. You can say generate random floating point numbers 0 to 100 with a normalized distribution, and it will do something like that for you. Yeah, it's very helpful. Okay, so let's actually use this knowledge. We are going to, first, I'm going to clear all of my output because I forgot to do that at the beginning. Okay, and then we're going to import a library called glob, and then numpy again, because we'll need both of those. Glob is a library that is used for traversing file systems, which is a fancy way of saying it fetches file names for you. So we have in this data directory in files for our data that are numbered 1 to 12. But let's say before we were just manually loading the first one all the time by like saying inflammation-01.csv. But let's say we wanted all of them and we wanted to load all of them in so we could do analysis on our entire data set. That's when we're going to want glob. So glob will let us say, okay, all of everything under the data directory that matches, let's even just do inflammation star. So we're using star as a wild card here, which says anything, any file name where the first part of it matches data/inflammation, and the second part of it can be anything. We don't care. Give me all of those files. And so glob.glob will go crawling through your file system and find everything that matches that pattern for you. And then returns it to you in a beautiful list. So we can see that in this case, it did fetch all of the inflammation files, and it tries its best to put them, I think it might sort them in alphabetical order, which in this case is also 0 to 12 order. But it also got this PNG that I had made during the last session, which we actually don't want because that's not like tabular data that we want to load in. So we can also use that wildcard to say, well, okay, give me everything that starts with inflammation and ends in .csv. Just give me the CSV files. And then that will get rid of that PNG that we don't want. Yeah.
The reason for importing numpy again.
Because we're going to use it later.
Okay.
The only reason. Yeah,
So
it's not required to use glob.
Oh, okay. But even if we already imported it earlier, we have to do it again.
No, you don't. If you already imported it earlier, you don't have to do it again.
Oh.
I just put it as a block here in case you want to like copy paste code and use it somewhere else kind of thing. Yeah. Okay, so this is the perfect time to be able to loop through all these files because now we have a list of all of the file names containing all of the data that we actually want to use. So we can set up a for loop. And this time I'm actually going to use some reasonable variable names, right? Because we want to actually be able to use this data. So I'm not just going to call it like thing or blah or whatever. The most common one in Python, usually when you have lists like this, is just to call it a file name because that is what it is. So we're going to say for file name in this list that I've just created and assigned to files, which I know contains all of our inflammation data. Let's just print it. You know, I want to make sure that it has what I want in it. Great, it does. It printed just fine. And you can see that every time it goes through that loop, it gives us just the singular file name back, right? Which is what we want. So what would I do if I wanted to load data from each file name and put it all into the same array? Maybe let's start. What would I do just to load the data out of the file name? Yeah, so what do I need to use to load the data out of the file name that we have in our for loop here?
The load text function.
Yeah, right, load text. We had been doing that before, so we can say data, whatever you want to call it, equals numpy.loadText and put in our file name, which in this case is file name. Is it file name or it might be F name? Yeah, that looks right. And then we need our delimiter. We can print data.shape. Make sure that we've got what we want. Right? Oops. Did I spell delimiter? Delimiter. Is it with an I? That doesn't look right. Hang on. Here, I spelled it right. Oh, it's miter. See? There we go. Nope. Typo. We'll get there. Haha. Okay. So unfortunately, though, the shape of our data at the end is only the size of a single one of our data files. So something has gone a little bit wrong. In the sense, and which we might be able to guess, is because every time we loop through this through a new file name, we're overriding the variable data with the new data. So by the end, it does have data in it, but it's only the data of the final file name. So how would we make sure that we actually end up with all of the data? What do you mean?
Like, put it in the for loop.
Yeah. Include what in the for loop?
The print data.shape. But I guess that doesn't give you the totals.
Yeah, so if we put it in the for loop, then it would print the shape of the data every time, but it would actually end up being the same because all of these file names have the same shape of data.
I assume there's like a concatenate function.
Yeah, exactly, right? There's an append function like we saw with the lists. So what I generally like to do in this kind of situation is define data as something out here. Maybe let's call it an numpy array, right? An empty numpy array. So that inside, I can just append to it every time. Maybe let's call this new data. And I can do something like, what is it? NP data equals np dot append data new data. Let me just double check that because sometimes I screw up the np append options. Yeah, okay.
How do you know if you're appending it to like, you're adding the columns to the side or you're adding the rows down? That makes sense. So if you have like two 5x5 arrays, how do you know it's turning into like a 5x10 or a 10x5 when you append them together?
Oh yeah, so you can, oops. So you can specify the axis on which you append things so that it either adds more rows or adds more columns if you want to. Sorry. You can soon fight me. There we go. Yeah. So you can sometimes specify with NumPy dot append, and if it's 1D, then it's simple, right? It just always sort of appends it to the end. There we go. Sorry about that. So if we do something like this, oops. Not right. Well, good. This is a perfectly good example. We see that obviously this is wrong, right? Because this seems to have flattened all of our arrays and put them into one extremely long uh, list equivalent, basically, which isn't quite what we want. So that's because our original array that we made was completely empty. So it's trying to match the old one with the new one, I believe. So I think if we do something like this and make it an actual size, 60, 40. Let's see if that does what I want. No, it does not. Okay. Well, NumPy arrays, man. We can also, maybe it's concatenate. Maybe that's why this is not. Oops. Files is right. Yes. Finding new data. Mo, do you see the clear error in what I'm doing here?
Are you trying to combine all the
Yeah, I just want to make it into one big array, and NumPy is not behaving with me.
you 0 to like 60 by 40, so I have to kind of, yeah, maybe just data equal to np dot empty, or
Oh, yeah, so
like limited to 60 by
yeah, that's what I did before, right? It isn't like this.
yeah.
But then if we do np.append here, it doesn't do what I expect it to do. It flattens all the data.
No, I think it's I remember there's like a vertical append and or something.
Okay, which is what you were asking about.
I can't remember the name. Oh, I think H stack or np dot H stack is a horizontal one, and then V stack will be, yeah.
Okay. Sorry, I gave you guys a bad example. Is it np.hstack or is it like a data.hstack like this?
Yeah, it's that new at the whole data. And some rubbish stuff.
That didn't work.
I think you also need another parenthesis around either and.
This?
Yeah.
No. All right, well, Mo looks at that. We can come back to this example. I gave you a bad one and I apologize. Anyway, let's at least use the for loop that we have to do something useful with it. If, let's say, we want to make a figure for each one of our new file names, right? We could do something like that. In this case, because we have like 12 file names, I'm going to limit it to something useful. So I'm only going to do the first 3. And then with our nice little for loop, we can take each of those 3 files, load it, plot it into its own figure, and then make like the average min max for each of our files. And you can see that was super fast versus having to write this out 3 different times or 12 different times for every single one of our file names. So having a for loop like that is really helpful when you want to repeat code over and over again, especially for something like for every file in this list, right? And this at least lets us start to look across these files and be like, something is suspicious with this data. Because like, look at how different these 3 sets of plots are. The first 2 seem to follow each other pretty well, but then the third set is wildly different. So like something's a bit off here. And what I also think is weird about this data is that the minima is a step function. Why is that? That seems weird. And the maximum is linear from 0 to 20 and 20 to 40, which is also super strange. Like that shouldn't be happening with real world data. Something has gone off the rails. Whereas in the third one, the average and the max look sort of like what I would expect an average and a max of real world data to look like. They're a bit messy, but they have some kind of trend on them. But the minimum is 0 all of the time, which is clearly wrong, right? Something has happened. And so that's where the for loop example, geez Louise, I'm all frazzled now. The if-else statements are going to be useful. Because we can use them to basically sift through this data without having to make all of these plots and like look at them manually. And we could say something like, well, if the minimum is always 0, I know this is bad data, so don't use it. Or if the maximum is linear between 0 and 20, I know this is bad data, so don't use it. Or flag it, or print a message to screen and let me know. Because if you're dealing with like thousands of patients, you can't sit here and look at every single plot from every single patient. So writing code that's able to sort of flag data as it comes in or sift through it like that is going to be really useful. And that's when we need the if-else statement. So the if-else statement is a similar syntax to the for statement, which is that you have the if statement and then a colon and then something indented. So if something, do something is how the if statement works, with the colon at the end, of course. And the if statement is always going to do something if what you're looking at is true. So if this thing I'm telling you is true, then do this thing. If it's not true, then it won't do the thing. So we can put anything in here, and this is when Booleans are going to become important again. So if 1 is less than 2, we know 1 is less than 2. So it's going to do the thing underneath the indent, which is a print that I put in here. Let me clear. Okay, there we go. And if you want to be a little wacky and sort of always force an if statement to be true, you can always just put the Boolean true there. Sometimes people will use this for debugging. If they really want a code path to be followed, they'll go and delete the old if statement and put in if true just to make sure you get to see what happens underneath the if statement. But you can see that, of course, the second one doesn't get printed because false is false, right? So any math statements like this will return true, false, depending on if it's true or false. So like 1 is not less than 0, so we get false. 1 is greater than 0, so we get true. And you can also use variables in the if statement itself. So if I set num equal to 37, I can check whether or not it's greater than 100. So I could say if num is greater than 100, do this thing. And then this is where the else statement comes in. So if num is not greater than 100, then do this thing under the else statement. Right? Num is not greater than 100, so it's going to print not greater. And then you can really start getting crazy and nest these things inside each other, right? So if num is 100, if num is greater than 100, do that. Else, if which is shortened to elif. Num equals 100, do that. Otherwise, num is less than 100. So you can really put a whole bunch of these inside each other and go through a bunch of different cases. So you could say, if patient name starts with D, then do this. If it doesn't start with D, but their last name starts with D, do this. If it doesn't start with D and their last name doesn't start with D, but their middle name starts with D, do this, right? So you can really sort of start to make pretty deep if statements here. You don't want them to get too deep or else your code starts to become illegible. If you have, 10 elif statements stacked on top of one another, then you might want to think about refactoring what your code looks like. And there is actually something called a case in Python, which might be a situation you might want to use in that situation. But all of the compare the operators for if statements that return Booleans, which also work outside of if statements, but the operators that return Booleans are all of your classic math operators. So greater than, less than, equal to requires two equal signs because otherwise the equal sign makes variables in Python. So you need two equal signs back to back in order to check whether or not something is actually equal to something else. The exclamation point equal does not equal the opposite of equal. And then you have greater than it or equal to and less than or equal to, right? So a lot of your sort of standard math operators. Now you can get kind of tricksy with sort of logic gates in Python by using and or as actual functions. So if you use and in an if statement, both of the things on either side have to be true in order for the if statement to trigger, or requires only one of the sides is true. So in this case, 1 is greater than 0, but -1 is not. So this will not trigger because only one of these things is true. But if we use an or statement, yeah, okay, 1/2 of that is true. So we will be able to do that. So this is also another way to sift through data. You could say, if my patient lives in Minneapolis or they broke their leg, then we want to do this thing with their data. But they don't have to both live in Minneapolis and have a broken leg. So we can do a quick example of how to use if statements to sort of sanity check this data. I'm just going to load our third data set here, which was that one that had the completely flat minima, which was a bit strange. So how could we check that, check for this weird flat minima thing? Any ideas? Well, let's start by, let's check if just the first entry is 0.
Like the minimum or like for one of them or for like the whole?
Yeah, so let's check if the minimum for patient 0 is 0.
Okay.
So we can start by fetching at least patient 0's data, right? So how did we get patient 0's data out of here?
assuming it's the same.
Yeah, they're made the same way.
Yeah, okay, so then it'd be 0, 0.
Yeah, so 0, 0 will fetch patient 0 on the first day.
You
But-
want all of it, so just colon.
Right, exactly. And then we can take the minimum of that, right? We can just check that. Okay, so that's 0. That is sort of what we saw in our plot. And then we want to say, if the minimum is 0, then, let me know. So what would we do next?
Do our if.
So if. So we just want to check whether or not this data equals 0 or not, right? So we can use that that equals sign here and say if it is 0, then our colon, because we always have to finish these kinds of statements with a colon. And I'm just going to print minima is 0. Double check your data.
Will all of them have a min of 0?
Hmm?
Because every patient starts with inflammation at 0 on day 0. Won't they all return 0 if you're checking by patient?
So let me pull back up our plots, right? So not always, right? So we can see like in our first 2 data sets. Oh, I see what you're saying, because we were checking across days.
Yeah.
Yeah, so in this case, yeah, because we said all of the data for patient 0 across all the
So
days.
they'll all have, yes.
Yeah.
If you wanted to find the error, you're trying to check across the days, so it would be colon comma 0 for your data, and then.
Yeah, exactly. So if we instead wanted to say for all patients across day 0, is the data 0?
Yes.
Yeah. So then you're right, you could do the colon and then the 0, right? So for all patients on day 0 is the minimum 0, and we can check that as well. And like you said, for across these 3 plots at least, the minima was always 0 on day 0 across the 3, so that's about what you expect. But now if we wanted to check, is it always 0 across all days? How would we change that?
Using a for loop going each day at a time.
Yeah, exactly, right? We can use our for loop to loop through all of the days. So we could say for, this is where your len is going to become helpful, right? Or we know the range, right? So we could say like for day in range 0 to, actually, yeah, because we do want the indexes. We went 0 to 40 for all of our days because we know it's 40 days. And then we have to indent our if statement here, right? So it's under the for loop. And then where would I put my variable day in this case?
Where 0 is now.
Yeah, exactly. Now in this case, this is going to print minima is 0 for every single day, right? So we might want to be a little bit more specific here, maybe. Want to say minima is 0 for day, and then put the actual number of the day. So we have a little bit more information. And now in this case, we know this is strange because it's 0 for every single day. So it does do what we expect. And then this is also where a bit of true false logic can be helpful. So true times false. Oops, print. So a kind of useful thing is that a little bit of logic with true and false. If you multiply true and false together, you're going to get false returned. True times true is true, false times false is false, true times false is false. So that is sort of helpful here, because if we say, okay, if it's equal to 0, we know that's true. But if just one of these is not equal to 0, then we don't want to return the message that your data looks weird. So we could do something clever here, like days are 0 or something. Set that equal to true. Hang on, that's not what I want. We could do something like, we think this through. Because we want it to return. No, I have to be clever. Times. If it's equal to 0, if they're all equal to 0. Sorry, I have to do the logic of this myself. So we basically want, if any day is not equal to 0, to return a false. So then at the end, we end up with false.
Did you just do not equal instead of equal?
Oh, yeah. Good call.
Oh, I wasn't paying attention. That's how you do not equal?
Yeah, so exclamation point equal is not equal. The other thing you can also add in an if statement is if not. So you can get really weird. If not this, not equal, right? You can really start screwing with yourself. We could do something like if not is sort of the equivalent here. And then let's say all days are 0 equals true. All days are 0 equals false. Something like that, you know. There are more clever ways to do this, but this is a nice way to do both a for loop and an if in the same thing. We could say if all days are 0, because it's just checking whether or not that is true. Right? Minima is weird. Check your data. You see, and there's all kinds of variations on this theme, right? Maybe we could also call this like data is good. And this data is good is false, right? Same thing. And then the other thing to know that I do want to let you know is that you can put white space like this in for loops and ifs, and it will continue in the same for loop. So adding white space there isn't going to end the for loop. But let's say we want to also check. So now we're checking for the minima always being 0, but then we also want to check for this weird behavior that we saw where the max was like 0 on day 0 and 0 on day 40 and 20 on day 20, right? So we could do a similar thing. Another if statement. This time we're checking the max. Otherwise, this could look the same, right? We still want all patients on that day. But now we want to be comparing the value of the max against the index, right? Because it was 0 at 0 and 20 at 20 and so we could do something like this, right? If that value ends up being equal to the day that you're in question, then that's giving you that weird linear behavior, at least up to 20. Let's make this an ELIF, right? Because if we're seeing this weird minimum, or if we're seeing this behavior, that's also bad. And I'm sure you could do some other sort of logic here, or the max, maybe, and p dot max to get the latter half data. This equals would be like if 40 is also 0, then it would be equals the right the length. So I guess 40 minus day. Oh, minus 1 because index is something like that. So 39 minus day. Because that would get the second half as well. So on index 39, that would be 0. Index 38, that would be 1, which is what we saw happening here. You could also add a catch for that. And you can have a hanging elif without an else statement at the end, but it's generally good practice to just call the last one in the list an else. Oops. Oh, forgot a colon.
Oh, there's a space. Else. Not like the space.
Else is like, you need to change it back to.
No, you're right. Yeah, you're right.
You don't have like.
Yeah, you don't. There's not a. There's. You're right. There's not a statement that goes with else. It just catches all other cases. So if none of the previous things were true, then do this thing. Cool. So that's how you could do something like that to catch weird data. And these can get really complicated, right? You could start checking for really strange things in your data. It's also a great way if you're making a Python script that has inputs to check that the inputs are reasonable. That somebody isn't giving you a number when you expect a string, or isn't giving you a really wild number when you're looking for a number between 0 and 10. That's when all these kinds of if-else statements are also a good way to sanity check inputs. Okay, last one. Unless anyone has any other questions about if-else statements. Like I said, you can sort of make these as complicated as you wanted to by adding extra logic into them. We could have changed this even, right, to add the ors in here instead of doing elifs. Could have said something like this. Oops, copy paste doesn't work. You know, and then we could have just deleted this. That's the same in our case. Okay. So function. A very common way to make your code shorter and repeatable. Because sometimes, like with the for loop even, the for loop sort of repeats your code over and over. A function can also do a similar thing, especially if it's something like a really complex calculation or something you don't want to type out every time. Uh, a function is a good way to make sure that you're always doing that complex calculation the same exact way every time because it's stored in this function and you're always going to call that function. So especially useful if you have like 10 grad students in your lab and they all need to be doing the same calculation, then putting it inside of a function that everybody has access to makes sure that everybody is doing it the same way. So that one grad student didn't accidentally put a typo in theirs, and so all of their numbers are off by 1 or something compared to everyone else, right? So functions, like many of the other Python statements, always have the colon at the end of their definition. And the way that you they're called instantiate one, is to use the keyword def for define, but it's short because we hate typing out everything in Python apparently. So we use def for define, and then you're going to put the name of your function, whatever you want to call it, the parentheses that functions require, and then you're going to put all of those inputs. So if I wanted to make a function that changes Fahrenheit to Celsius, that's a pretty straightforward one. I don't need any other input except the temperature you would like me to change. So it only has one input. And then you can do whatever you would like underneath of it, but functions generally also return something back to the person who called them, right? So in this case, I know that the person who is calling this wants the temperature in Celsius. So I'm going to return that number back to them by using the call return. And a function can return just about anything. It can return a number, a list, an array, whatever makes sense for your function. You can also do something like cells temp equals, and maybe I'll put this like that. And then I can return cells temp. And that's going to do the same thing if you want to make your code look a little bit cleaner or if you need to manipulate something a couple times. So if we convert 32 to Celsius, we're going to get 0, which is great. And you can also give your inputs to your function some defaults, like we had talked about before. So if nobody provides a temperature, I'm going to say that the default is 32. So if we just called this, oops, need to reinstantiate the function. It'll still give us that 0, because if you don't provide it with an input, that's going to assume that you meant 32. And if for some reason you wanted your function to take a whole bunch of inputs, you just comma separate them. So maybe it wants to take a temp and is it sunny? And even though I'm not using is it sunny, it is technically required by my function. So if I just try to give a number for the temperature, it's going to yell at me because I'm missing the other input, is it sunny? Unless, of course, we gave it the default. And then I don't have to provide it. So if we wanted to change this to also do like a Celsius, right? Celsius to Fahrenheit, right? So we need a definition. Let's call it something reasonable. Celsius to Fahrenheit. I mean, Kelvin. What kind of input are we going to need? Temperature. Yeah, something. Temperature, please. Temperature in Celsius, maybe. And the colon at the end. And we can, luckily it's even easier than converting between Fahrenheit and Celsius, right? Just add 273. Oops, that's not a plus sign. So we can use Celsius to Kelvin. One. Right. And just like for loops or anything else, you can do whatever you want inside of this function as long as it's under the end. So if we wanted to convert Fahrenheit to Kelvin, we could say, great, you gave me this Fahrenheit value. I already have a function that converts Fahrenheit to Celsius. So I'm just going to go ahead and call that because I don't want to type it again. Or I don't remember what the fraction that it's supposed to be multiplied by is. So I'll just go ahead and call it with a function I already made. And then I'll add 273 at the end because I know that it works that way. Even better, I could just call Celsius to Kelvin here. Right? Because I also already have that function. So you can just have a function that calls two other functions. And that's a perfectly reasonable thing to do.
So for that one, if you like put in, it'll give out two numbers. If you give it one, like if you give it 0, it'll spit out two numbers.
Are you talking about this one?
Yeah, the Fahrenheit to Kelvin.
No, so we're giving it the temperature in Fahrenheit.
Yeah.
It's doing some internal math, but it's only returning this one variable. So it's only going to return, you can see when we printed it, 273. Even though it made additional variables on the inside, it's not returning the other ones. So you're not going to see that at the end as part of the end result. I could return both of them if I wanted to, but that's not what the function does, right? So that would be a weird thing as a user to get at the end if I expected it to give me a number in kelvins and it gave me two numbers, right? So that's what I mean by you can do whatever you want. Like I could make an array here that does nothing. And you're never going to see that because it's not involved in the return statement. Okay. So something to keep in mind though, is the scope of the variables that you create, which comes up a lot when you're dealing with functions. So I've defined this temp pretty freely here, just in a cell like this, not under anything. It's not even under a for loop. That's an example of a global variable. It's going to be available throughout this Jupyter notebook because I just instantiated it with nothing else surrounding it, right? So I can print it here without an issue. It's going to tell me that is 32. But this variable temp underscore C was only defined here inside of this function, and it was also defined here inside of this function. But if I try to access it, it tells me that it's not defined. And that's because it's considered a local variable. So variables that you define inside of functions are only available inside of that function. And as soon as you get outside of it, they're not going to be available again. So if I define temp underscore C inside of farad to Kelvin, I'm not going to be able to access it generally. It's only going to exist while that function inside of that function, which is nice to help to make sure your variable names don't collide with one another. For example, if I called something data inside of a function, this other thing I called data out here is going to be affected and that kind of thing. So we can use functions, like I said, to save space, to repeat code, make sure that code is always consistent. So I could import all of my usual suspects here, matplotlib, numpy, and glob, and then take all of that information that we had used to plot the sort of three plots side by side for the average, max, and min, and throw it into a function. I'm going to call it visualize because it's going to take a file name and it's going to plot the min, max, and average on a nice plot and throw that back, right? Well, in this case, it's not even returning it, it's just showing it on your screen. So this is nice, right? Maybe, I'm not sure if this will copy and paste correctly in the Zoom chat, but I will put it in there for you because it's a pretty big block. Yeah. So in this case, now we have a block that does the plotting, and all it takes is a file name. So we can give it any of our information file names and expect that it will show all of the plots that we want, right? So in this case, I'm going to use our nice little for loop to pull out our first three file names and make sure that it works, make sure that it makes the plots that we expect it to. And indeed, these match the ones that we had seen before. So we know that this is working properly. But now, instead of having to copy paste this 3 times or even put it in a for loop, this is a function that we can use throughout this code. Maybe we we wanted to plot all 12 of the inflammation data sets, or maybe we got new data that we wanted to plot. We can just continue to use this one function without having to go back in like 3 different places to make sure that the plotting code does what we expect it to. Like if I wanted to change this plot to be green instead of blue, I would have had to go to 3 different locations in the previous code to make sure it was always green. But now I just have to come here in this one function, change it, and be sure that it'll always be green from here on out. So that's sort of the power of functions here. We could, using our inflammation data as well, make a function that checks for that weird data, right? If we threw that under a function, we could call it in the visualize code and just not make plots for the data that look weird, or only make plots for the data that look weird, right? And so that's a case that you could call this function within a function and have it be useful. Like basically do a little sanity check on your data before plotting it to make sure that it looks the way you expect it to. And of course, the possibilities are endless here. So any questions on that? Are we good to move on? I still hear typing. So I wasn't sure if we were okay to keep going or not. Okay. So the other thing about making functions is that you do always want to make sure that once you make a function, you remember later what the heck it was for. Like, why does this function exist? What does it do? I don't know. So one way is, of course, to add these little comments that I've had throughout here, right? I always put these little comments in the code to sort of give you little prompts about what it is that I'm doing. And you can do that inside of functions too. There's no reason you can't put comments inside. So like I could take this visualize function and be like, load data. And then, I don't know, start figure, add individual plots, right? And so that's always helpful to sort of let you know what's going on as you sort of continue throughout a function. It's generally helpful in code. But the important thing about functions is that you can actually also add additional documentation. So all functions in Python will respond to the, I don't know, Uber function help. So if you put the name of a function inside of help with the parentheses, it's going to give you information about that function. So we made the function Fahrenheit to Celsius. So if I type help into there, it's not going to give me a ton of information, but it's at least going to tell me the name of the function and the inputs that it expects, right? So those two inputs that were at the top of the function definition. But you can see if maybe I do like np.max. Oops. Oh. NumPy. I can type. There's a whole bunch of information associated with numpy.max. And it tells you, oops, scroll function, tells you what it expects, parameters, all of the different inputs, and all of the things that inputs can be. So you see, apparently Max has a keep dimensional Boolean option that we never used. Or it even gives advice on like other similar NumPy functions we might want, like maximum and fmax and argmax. And there's even some notes here at the bottom. And all of this is associated specifically with the Python help function. So you want to make sure that if you make a function that it has all of this same documentation or similar documentation to let users know what the heck it is and what it does so that people can actually use it. Otherwise, you'll make it for yourself once and nobody else will ever be able to know what they're supposed to be doing with it. So one of the ways to do this is you can provide notes, like I said, with the little hashes. If you put them directly above a function call, help will pull that information and will print it out with the function. As long as it's directly above the function definition without any white space. As soon as you add any white space there, it's not going to pull it anymore. So it's a little bit faulty, it's a little bit specific. The more common way and the quote unquote proper way to do this is to use what's called a doc string. So you'll see this across more standardized code that uses specifically the 3 quotation marks side by side by side. And that's what lets the help function know that this is documentation that it should pull. So you can see now it's pulling this specific line because it's been listed as a doc string at the top of the function. And if we want to make it even more official, we can do proper things like telling it what the inputs it is that it expects and the type of input it'll take. It'll take like an integer or a float input because we can't take strings, right? We were doing math with it. So if we tried to multiply the letters 0 by 3, it's not going to do what we want it to. So it has to be an integer or float. And we know that the number that we're returning is a float. And then we can even give it a little example, bar Celsius of 32 should give you 0. And that's sort of the proper way to document your functions. So generally, 3 things come with the documentation on functions: a simple description, followed by what the inputs and outputs of the function are, followed by an example of the usage of the function. And so if we run this, you can see the help function will print out all of the relevant information. Okay, that's actually the end of it. I'm leaving a little bit of time here at the end for people to ask any questions. It can be specifically about your data if you would like it to be.